Hey guys, 200 members unlocks a Discord, 500 unlocks a new series, 1000 changes how every video looks. It starts with one decision. Patreon link is in the description.
There is a moment just before sleep when the body stops pretending it has somewhere to be. The muscles go soft, the room goes quieter than it actually is, and sometimes in that particular kind of stillness, a thought arrives, not a loud one, just a small unhurried thing, about how much of the universe is moving right now without making any sound at all. That thought is a decent place to start. Guys, real quick, before we begin, someone just stepped up to the co-creator tier on Patreon. And that means we are now only 23 members away from the number that makes this channel stable. You guys are the fuel behind everything that happens here. Without the people who choose to support, this channel does not move forward. Every single person who joins shifts something real. On Patreon, there are over 50 episodes, comparison files on some of the most fascinating objects and phenomena in the universe, conversations where you can reach me directly, and a lot more. We are 25,000 people here. Only 23 co-creator members is what stands between this channel and stable ground. If you want to be part of closing that gap, the Patreon link is in the description. 2 galaxies are moving toward each other right now, not metaphorically, not in some abstract cosmological sense that only matters to people with whiteboards. Literally, physically at this moment, somewhere out past the reach of anything we could name from here, 2 systems, each containing hundreds of billions of stars, are closing the distance between them. Have been for a long time, will continue for longer still, and when they finally arrive at what we call a merger, what happens will be, and this is the part that takes a moment to actually absorb, almost entirely silent, almost entirely empty, almost nothing in the tactile sense at all. The word collision is wrong, it has always been wrong, but it is the word that gets used, and it carries weight it hasn't earned. It suggests impact, it suggests the kind of event you feel in your chest. 2 things are meeting fast: resistance, noise, consequence immediate and visible. A collision is something you flinch at. A galaxy merger is something you would not notice if you were standing inside one. That deserves to sit for a second. Stars are not close to each other. This sounds obvious until you try to hold the actual numbers. In a galaxy like ours, the nearest star to the Sun is roughly 4 light years away. 4 light years. If the Sun were the size of a grapefruit sitting on a table, the nearest neighbouring star, also a grapefruit roughly, would be somewhere around 25,000 kilometres away. Not in the next town, not on another continent. On the other side of the planet, maybe further. And those are neighbouring stars. The space inside a galaxy, between its members, is not crowded. It is, by any meaningful standard, an almost absurd amount of nothing. So when 2 galaxies drift into each other, what happens to all that nothing? It stays. Mostly. The 2 systems interpenetrate. That is the technical word, and it is a strange one. They pass through each other. Not like 2 clouds colliding, not like 2 liquids mixing, but more like 2 swarms of insects flying through each other in opposite directions, without any 2 individuals ever making contact. The stars do not hit. The probability of any single stellar collision during a galaxy merger is, depending on the densities involved, somewhere between vanishingly small and essentially 0. You could watch it happen if you had a few 100 million years and a vantage point sufficiently far away, and you would see 2 diffuse, sprawling structures move into and through each other, while the individual points of light inside them remained entirely intact. What does interact is gravity, and gas, and dark matter, and those interactions are where everything interesting lives. Gravity does not require contact. It reaches. It pulls at the shape of things from a distance, and when 2 galaxies begin to close in on each other, long before their outer edges have technically overlapped, the tidal forces begin. Stars on the near side of each galaxy feel a stronger pull toward the approaching system than stars on the far side. That differential, that stubborn, uneven tug, begins to stretch and distort the structure of both galaxies. Long streamers of stars get drawn out, arcing tails extend into the surrounding dark. Bridges form between the two systems, thin connections of material pulled gravitationally from one toward the other. The galaxies begin to look wounded before they have even truly met. This takes time, not human time, not the kind of time you can feel accumulating. The first close pass, the initial moment when the centers of the two galaxies are nearest to each other, can take hundreds of millions of years to arrive from the point at which the approach became inevitable. And then, after that first pass, the galaxies do not immediately merge, they separate again. They move back out to some distance, slow, stop, turn around under the pull of their own shared gravity and fall back in. Sometimes this happens more than once. The whole process, from first gravitational influence to final coalescence of the two nuclei, can unfold across 1 to 2 billion years. 1 to 2 billion years. It is worth pausing on that. Not because the number is decorative, but because it changes what the word merger actually means. This is not an event. It is an era. It is a geological age happening in 3 dimensions at galactic scale. And during that entire unfolding, the stars inside both systems are largely going about their individual lives, burning hydrogen, dying, becoming white dwarfs or neutron stars or, at the massive end, black holes, with no particular awareness that a merger is occurring. They are passengers. The drama, such as it is written in gravity and gas, not in stellar contact. The gas is different. Gas is not a point. Gas is a medium, a thing that occupies volume, that can compress and heat and be pushed. When two gas-rich galaxies begin to interpenetrate, the gas from each system does interact with the gas from the other. It shocks. It heats. It can be compressed into configurations that matter, that eventually, under the right conditions, lead to the collapse of giant molecular clouds and the ignition of new stars. This is where the starburst idea comes from. This is where the promise of the merger lives. But whether that promise gets kept, whether the gas actually falls into new stars or instead gets heated, scattered, expelled, locked away in states too warm or too diffuse to collapse, that is a much longer, much more conditional story. The merger is not a guarantee of anything. It is a set of conditions, a pressure applied, an occasion. What the occasion produces depends on what is already there, on what has already happened to the gas, on how massive the black holes at the centers of both systems are, and how much they will wake up when the inflow begins, on whether the geometry of the approach generates the right torques at the right moment, on whether the dark matter halos are dense enough, the orbits close enough, the gas fractions high enough to sustain what begins. Most of the time, they are not. Most of the time, the merger produces less than expected, often considerably less, sometimes almost nothing new at all. The night these two galaxies started falling toward each other, nothing exploded, nothing announced it. Some slight rearrangement of trajectories, some imperceptible shift in the tidal field felt across distances that have no human scale. And now they fall. They have been falling, and somewhere in what follows that fall, in the gas dynamics and the black hole feedback and the slow starvation of the cold reservoirs, is the reason that some of the largest structures in the known universe are also, quietly, some of its most sterile. The word for what is coming is not collision. It never was. Something moves first, not both galaxies simultaneously, not in any synchronized way. One is traveling, the other is, in some sense, waiting, though waiting is the wrong word because waiting implies awareness, and there is none of that here. There is only mass and the curvature it makes in space, and another mass following that curvature inward, closing the distance that has existed between them since before either galaxy had its current shape. The approach is not fast. Nothing at this scale is fast in any way that maps to the human understanding of that word. But it is committed. Once two sufficiently massive systems are gravitationally bound to each other, the outcome is not a question. Only the timing is. The first pass is when the centers of the two galaxies reach their closest point for the first time, pericenter in the technical language. And everything that happens at that moment, everything that makes the first pass worth naming as its own event, comes from the differential. Tidal forces are not mysterious, they are just gravity being uneven. When a massive object approaches, the side of your system nearest to it feels a stronger pull than the side farthest from it. That difference, not the pull itself, but the difference across your extent, is what stretches things. The moon stretches Earth's oceans this way. Earth stretches the moon's rocky interior. And a galaxy, at pericenter, stretches the other galaxy across a spatial scale that makes oceanic tides look like a slight lean. The outer stars on the near side get pulled harder. They accelerate toward the approaching system. The outer stars on the far side get pulled less. They lag behind. And that lag, accumulated over the timescale of the encounter, draws them outward into a long, slow arc, trailing behind the galaxy's center of mass. These are the tidal tails. They are not flung. Nothing here is flung. They are drawn, reluctantly, incrementally, by a force that never announces itself, just persists. Bridges form too between the two systems. Material from each galaxy pulled toward the other, spanning the gap between them in thin, diffuse filaments of stars and gas. If you were looking at this from a distance enormous enough to see both galaxies at once, you would see them connected, tethered, in a way that looks almost deliberate. Two sprawling structures with something stretched between them, the geometry changing slowly as the encounter continues. And the gas, the cold molecular gas that lives in the disk of each galaxy, distributed along the spiral arms, settled into a more or less flat rotating structure. The gas responds differently than the stars do. Stars behave like particles during this encounter. They follow gravitational trajectories without interacting with each other in any physical sense. Gas does not have that luxury. Gas has pressure. Gas has turbulence. When the disk of one galaxy passes through the disk of another, even at the low contact densities involved in a first pass, the gas experiences shocks. Not the kind of shock that carries drama. The kind of shock that is a specific physical state, a region where material moving at one velocity meets material moving at a different velocity, and the transition between them is abrupt enough to compress and heat the gas at the boundary. These shocks can squeeze portions of the gas to higher densities. They can push clouds that were sitting quietly in rotational equilibrium into a slightly denser configuration than they were a moment before. Under the right conditions, and this is the part that matters, that compression can push a molecular cloud past the threshold for gravitational collapse. Stars begin to form. Not many, not quickly. The starburst, if it happens at all during the first pass, is modest. A flicker, a hesitant brightening in a few dense regions where the compression happened to land on gas that was already close to the edge. This is where I want to be careful, because the temptation is to make this sound like more than it is. The first pass does not produce a starburst in the way the word starburst usually travels in popular descriptions of mergers. It produces an enhancement, a nudge above the galaxy's baseline rate of subformation. Studies of close galaxy pairs, systems caught at separations consistent with having just completed or approaching a first pass, show elevated star formation rates, but elevated in the range of factors, not orders of magnitude. Maybe twice the rate, maybe 3 times, not 10, not 100. Not the kind of number that suggests something is burning out of control, which is strange if you think about what just happened. 2 systems containing hundreds of billions of stars and enormous reservoirs of cold gas have just swept through each other. The tidal forces have been significant. The shocks have been real, and the outcome is a modest uptick in star formation in a few concentrated regions, mostly confined to the inner disk and the overlap zone, while the rest of the galaxy continues more or less as before. The gas in the tidal tails is moving outward. That gas is not forming stars efficiently. It is low density now, spread thin across the length of the tail, and low density gas does not collapse easily. The gas that got compressed in the overlap region may form some stars, but not all of it. Most of it gets heated enough to become temporarily resistant to further compression. And the stellar feedback from even the modest new star formation, the radiation and winds, and eventually supernovae from those young stars, pushes back against the very regions where more star formation might otherwise have continued. After Placenta, the two galaxies do not stay together, they separate. The angular momentum of the encounter carries them back out to a large separation, sometimes almost as large as where they started, for gravity decelerates them again until they begin to fall back inward for the second pass. This interval between first pass and second approach can last hundreds of millions of years. During that time, the tidal tails persist, the bridges thin and disperse, the newly formed stars from the first pass compression are already aging, and the galaxies themselves are structurally changed, more disturbed, less symmetric, their outer disks frayed and irregular, but still recognizable as the systems they were. The first pass does not decide anything. It sets up the conditions for what follows. It moves gas around, redistributes angular momentum, disturbs the stability of both disks, and seeds a faint signal of star formation that will be overwhelmed or consumed or shut down entirely by the larger processes that the eventual coalescence will unleash. It is, in the end, more of a beginning than an event. What it begins is less straightforward than it looks. The assumption did not come from nowhere. That is the first thing worth saying. It came from observation, from logic, from simulations that were genuinely sophisticated for their time, and from a chain of physical reasoning so internally consistent that questioning it felt, for a while, like questioning arithmetic. The idea that galaxy mergers reliably trigger bursts of star formation was not a careless extrapolation. It was a conclusion, one that accumulated evidence held up under scrutiny, and became, for a generation of researchers, something close to settled ground. Understanding why it seemed so certain is not a detour. It is the whole point of this chapter. Start with the infrared sky. In the 1970s and 1980s, as infrared astronomy became properly possible, as detectors improved enough to see through dust and into the warm radiating interiors of galaxies, something kept showing up that nobody had fully anticipated. Certain galaxies were producing extraordinary amounts of infrared light. Not optical light, not radio emission, but heat. Thermal radiation from dust that was itself being heated by something intense happening inside. These were the luminous and ultraluminous infrared galaxies, LIRGs and ULIRGs in the shorthand, and they were putting out energies that rivaled or exceeded the output of quasars in some wavelength ranges. When astronomers looked at them in optical light too, a pattern emerged. A large fraction of these infrared luminous systems were disturbed. They had irregular morphologies, tidal tails, double nuclei. The structural signatures of two galaxies that had recently encountered each other or were still in the process of merging. The correlation was not perfect, but it was strong enough to be persuasive. The most intense star-forming galaxies in the observable universe appeared to be merging galaxies. The merger, it seemed, was doing something to the gas, something that produced not just ordinary star formation, but an almost frantic acceleration of it. The physical explanation followed, and it was elegant in the way that good physics often is, not complicated, just clear. When two disk galaxies approach each other, the gravitational interaction is not uniform across either system. The near side of each galaxy feels a stronger pull than the far side, and this differential, this tidal stretching, does something specific to the gas that it does not do as effectively to the stars. Gas has angular momentum. Ordinarily, that angular momentum is what keeps it in stable circular orbits within the disk. Remove the angular momentum, and the gas has nowhere to go but inward. And tidal torques, generated by the asymmetric gravitational field of the approaching companion, are extraordinarily efficient at removing it. The gaseous bars that form during a merger, elongated, unstable structures driven by the tidal perturbation, lose angular momentum to the stellar disk around them through gravitational torques. The gas that was rotating contentedly in the outer disk finds itself in radial orbits, falling inward. It accumulates in the central kiloparsec, the density rises, and in gas dynamics, rising density is a fairly direct path towards star formation, because the Jeans criterion, the threshold above which a gas cloud's self-gravity overcomes its internal pressure and begins to collapse, depends on density. Pack the gas more tightly and collapse becomes not just possible but unavoidable. This was the logic, and it was not wrong exactly. It described a real process. Tidal torques do strip angular momentum, gas does fall inward during mergers, nuclear densities do increase, star formation does respond. The early simulations of the 1980s and early 1990s, which were by modern standards relatively coarse but which captured the large-scale gravitational dynamics reasonably well, showed exactly this sequence playing out. Gas piled into the centres of merging systems, star formation spiked. The simulated merger remnants looked, in their broad properties, like the infrared luminous galaxies being observed. The match between theory and observation was good enough that the next step, the generalization, seemed almost automatic. If the mechanism was tidal torques driving gas inward, and if tidal torques were an inevitable feature of any major merger between gas-containing galaxies, then the starburst was effectively guaranteed. Not a coincidence, not a special case, a predictable consequence of the physics. Merge two gas-rich galaxies and you get a burst of star formation. The logic was load-bearing enough that entire theoretical frameworks for galaxy evolution were built on top of it. What the early picture underweighted, and this is where it began to quietly accumulate debt, was feedback. Not because feedback was unknown. Stellar feedback, the radiation and winds and supernovae produced by young massive stars, had been part of galaxy formation models for a long time, but in the context of mergers, it was treated as a secondary effect, something that modified the starburst rather than something that could interrupt or prevent it. The gas was going to fall in, the stars were going to form, the feedback was going to do what feedback does, blow some gas around, heat some of it, slow the rate a little, but the fundamental picture of merger-triggered starburst remained intact underneath. The other thing the early picture underweighted was diversity. Not all mergers were gas-rich. Not all approaching galaxies had intact fuel-laden disks. Not all orbital geometries produced the same torques at the same efficiency. Not all black holes at the centres of these systems were the same mass, and not all of them would respond to the infalling gas in the same way. The LIRG and ULIRG observations that had anchored the assumption were, almost by definition, a biased sample. They were the mergers bright enough in the infrared to be noticed and catalogued, which meant they were the mergers where star formation was already exceptional. The quieter mergers, the ones where the gas fell in and nothing much ignited, were harder to see and easier to overlook. None of this was obvious at the time, and I think it is worth resisting the impulse to treat the original assumption as naive, because it was not. It was a reasonable inference from available data, grounded in real physical mechanisms, supported by the best simulations of the era. The people who built that picture were not missing something careless. They were working at the edge of what was knowable. What changed was not insight exactly. It was resolution, better simulations, more complete observations, a larger and less biased sample of merging systems at different stages and different gas fractions. And as the picture sharpened, the clean guarantee of the starburst began to develop acceptance, then more exceptions, then enough exceptions that the exceptions stopped being exceptions and started being the question itself. Why, when the mechanism is real and the physics is sound, does the starburst so often fail to arrive? That is what the rest of this needs to work through. Not every merger fails to ignite. Some of them burn, some of them produce star formation rates so elevated above the galactic baseline that the word starburst is genuinely earned. Not as a loose description of mild enhancement, but as a real characterization of something running hot, consuming fuel at a rate the galaxy has not seen before and will not see again after the gas is gone. These systems exist. They have been observed, catalogued, studied in detail. And what makes them different from the mergers that produce nothing much, what separates the furnace from the cold collision, is not one thing but a specific assembly of conditions that have to arrive together at the right moment, in the right order. Start with the gas. This is the non-negotiable part. A starburst requires fuel, and the fuel for star formation is cold molecular gas. Not warm gas, not ionized gas, not the diffuse atomic hydrogen scattered through the disk. Cold, dense molecular gas organized into clouds massive enough to collapse under their own gravity. If the merging galaxies are gas-rich, if both progenitors carry substantial reservoirs of cold molecular gas in their disks, then the raw material is present. If they do not, the conversation is largely over before it begins. The fraction of gas relative to total baryonic mass, what astronomers call the gas fraction, is the single most predictive variable in whether a merger produces vigorous star formation. High gas fraction, possible. Low gas fraction, almost certainly not. But gas fraction alone is not enough. Gas sitting in a stable disk, rotating in equilibrium, does not collapse into stars particularly quickly just because another galaxy is nearby. Something has to disturb the equilibrium. Something has to move the gas out of its comfortable circular orbits and into configurations where density rises fast enough to trigger gravitational collapse. That something is angular momentum loss, and the efficiency of angular momentum loss depends heavily on the geometry of the encounter. Orbital geometry is where things get specific in a way that matters. When two disk galaxies approach each other, the orientation of each disk relative to the orbital plane of the encounter and relative to each other determines how strongly the tidal torques couple to the gas. A prograde encounter is one where the spin of the galaxy's disk is aligned with the orbital angular momentum of the pair. In this configuration, the tidal perturbation from the companion stays on the same side of the disk for an extended period during the close approach, building up a sustained resonance between the orbital motion and the disk's own rotation. That resonance is efficient at generating the non-axis symmetric structures, the bars, the spiral distortions, the elongated gaseous features that channel angular momentum away from the gas and allow it to fall inward. A retrograde encounter where the disk spins opposite to the orbital direction does not build that resonance. The perturbation sweeps across different parts of the disk too quickly to accumulate the same effect. The tidal tails are shorter, the inflows weaker, the central gas accumulation less pronounced. Some star formation enhancement still occurs, but it is considerably milder. The geometry suppressed it. The most favourable configuration, the one that consistently produces the strongest starbursts in simulations, is prograde, where both disks are spinning in the same direction as the orbital motion of the pair. In this case, both galaxies experience efficient angular momentum loss simultaneously. Both funnel gas inward, and the overlap region between them during the closest approach becomes a site of gas collision from two directions at once. The compression is stronger. The density rise is faster. The starburst, when it ignites across a larger volume. Then there is the mass ratio. In a merger where both galaxies are close to equal in mass, a ratio approaching 1:1, the tidal forces are symmetric. Each galaxy perturbs the other with comparable strength. The structural distortions are deep and mutual. In a highly unequal merger, where one galaxy is much more massive than the other, the smaller system is strongly disrupted while the larger one barely notices the encounter. Its disk is too massive, too self-gravitating, too stable to be significantly deformed by the gravitational pull of a much lighter companion. The inflows that would otherwise drive gas to the centre are weaker. The non-axis symmetric features less pronounced. The starburst correspondingly muted or absent. Equal mass major mergers, mass ratios of roughly 3:1 or tighter, are where the conditions align most readily. There is also timing within the encounter itself. The first close pass generates some inflow and some star formation, but the most intense activity tends to occur later. During the final coalescence, when the two nuclei are merging and the gas that has been accumulating into both central regions over the course of the interaction is finally compressed together in a volume small enough that collapse becomes rapid and widespread. The peak starburst in systems where it genuinely fires often arrives in this final phase, which means that a galaxy merger has to survive long enough, with enough gas remaining unconsumed from the earlier passes, to reach that moment with sufficient fuel still available. Gas consumed too early, or expelled by stellar feedback from the first pass enhancement, is gas that will not be present for the peak. What this produces, when all the conditions are met, is something genuinely extreme. In the most intensely starbursting merger remnants, the ultra-luminous infrared galaxies, star formation rates can reach hundreds of solar masses per year. The Milky Way, in its current quiet state, forms roughly 1 to 2 solar masses of new stars per year. A major wet merger at coalescence with prograde geometry and high gas fractions in both progenitors can push that rate up by factors of 100 or more. The infrared luminosity climbs. The dust heats up as young massive stars pour radiation into it from the inside. The system glows in wavelengths that optical telescopes would miss entirely. It is worth sitting with that number for a moment, hundreds of solar masses per year, because it clarifies what is actually being described here. This is not a mild enhancement. This is a galaxy essentially spending its entire cold gas reservoir in a geologically brief interval. The gas consumption timescale in the most extreme starbursting systems can drop to a few 100 million years, which is short by galactic standards, which means the starburst is not just intense, but finite. It burns through what is available, and then it stops one way or another, either because the gas is gone, or because something shuts it down before the gas runs out. That second possibility, something intervening before the fuel is consumed, is where the story becomes more complicated, because the same conditions that allow a starburst to fire also allow the supermassive black holes at the centres of both merging galaxies to feed. The infalling gas does not arrive exclusively at star-forming regions. Some of it, the fraction with the lowest angular momentum, falls all the way into the nuclear region and onto the accretion disk of the black hole. The black hole grows, and a growing black hole does not stay quiet. What happens when it wakes up is a separate question, but it begins to matter in the systems where the starburst does fire, almost immediately. About 45 million light-years away, in the constellation Corvus, 2 galaxies have been in the process of merging for the last few 100 million years. They are close enough that ground-based telescopes in the 19th century could already see something was wrong with them. The morphology irregular, the structure doubled, the long curved extensions trailing outward in a way that no isolated galaxy produces. John Herschel catalogued them in 1833. The name came later from those extensions. 2 long tidal tails arcing outward from the system in opposite directions, curving like the antennae of an insect caught mid-gesture. NGC 4038 and NGC 4039, the Antennae galaxies. The nearest example of a major merger between 2 spiral galaxies that the observable sky currently offers. That proximity matters enormously. Distance in astronomy is not just a measurement, it is a resolution constraint. The closer a system is, the more detail can be extracted from it. The more specific the observations can be, the more precisely you can locate where things are happening and where they are not. At 45 million light-years, the antennae are close enough that Hubble and Spitzer and ALMA could look at them not as a single blurred event, but as a spatially resolved system. A merger with internal geography, with regions that can be examined individually, compared, argued over. That spatial resolution is exactly what made what was found there surprising. The star formation in the antennae is not where the gas is densest. That sentence needs a moment, because it runs against what the standard picture would predict. In the simple version of the merger starburst story, or the one built on tidal torques driving gas inward and nuclear densities rising until collapse becomes unavoidable, the most intense star formation should be concentrated at or near the galactic nuclei. That is where the gas accumulates. That is where the densities peak. If the mechanism is gas compression followed by collapse, the nuclei are the obvious location for the output. Spitzer Space Telescope observations of the antennae, published in the mid-2000s using the infrared array camera, map the star formation activity across the system at wavelengths that cut through the dust, obscuring the optical view. The non-stellar infrared emission, the signature of dust heated by young, hot, newly formed stars, was brightest not at either galactic nucleus, but in the overlap region between the two disks, the zone where the two systems are currently interpenetrating. Off-nuclear, distributed across a region that sits between the two centers rather than inside either of them. The nuclei themselves have lower star formation rates than the surrounding overlap region, despite containing abundant dense gas and dust. Dense gas and dust present star formation rate lower than expected. That is not what the simple picture produces. It suggests that something about the conditions at the nuclei, the turbulence perhaps, or the mechanical energy being injected by whatever is happening in those compact central regions, is working against collapse rather than accelerating it. The gas is there. The stars are not particularly forming there. The stars are forming in the overlap zone, where the two disks are meeting, and where the shocks from that meeting are compressing clouds into configurations past the threshold for collapse. Hubble imaging told a complementary story in optical light. Thousands of compact blue sources distributed across the merger, concentrated especially in the overlap region and along the inner portions of the tidal tails, young massive star clusters, some of them containing millions of stars formed in the last few tens of millions of years. The sheer number of these clusters, and their distribution, confirm that the star formation triggered by this merger is real and substantial. The estimated rate across the whole system runs around 20 solar masses per year, which is roughly 10 to 20 times the Milky Way's current rate and substantially elevated by any normal galactic standard. But, and this matters, 20 solar masses per year is not the extreme end of what mergers can produce. The most intensely starbursting systems reach hundreds of solar masses per year. The antennae, for all their prominence in the literature, are not a maximal starburst. They are a vigorous but intermediate case, and they are still in early stages of the merger sequence. The two nuclei have not yet coalesced. There will be additional passes, additional compressions, additional opportunities for the star formation rate to climb. The gas consumption timescale, the time it would take the current star formation rate to exhaust the available molecular gas reservoir, has been estimated at around 700 million years. That is roughly comparable to the remaining merger timescale, which suggests that the antennae are in a race between consuming their fuel and completing their coalescence, which is not a trivial observation. It means that by the time the two nuclei actually merge, the gas reservoir that would fuel the final coalescent starburst may already be substantially depleted. The star formation happening now in the overlap region is drawing on the same pool of cold gas that would otherwise be available for the most intense phase of the merger. Whether enough gas survives to produce a strong nuclear starburst at final coalescence, or whether the antennae arrive at that moment gas poor and already cooling, is something the current observations cannot resolve. The system has not finished yet. What the antennae have revealed, more than any other single system, is that the relationship between merger and star formation is geometrically specific. Where the star formation occurs matters, and where it occurs is not simply determined by where the gas is most abundant. The overlap region is not necessarily the densest part of the system, it is the most dynamically disturbed part, the zone where the meeting of two disks generates the shocks and compressions most conducive to rapid cloud collapse. The distinction between gas density and gas disturbance is not a subtle one. It changes the entire picture of how and where stars form in a merger, and it suggests that local physical conditions, turbulence, shock geometry, the direction and speed of gas streams colliding, matter as much as total gas mass in determining the outcome. There is something in this system that resists easy summary, and I keep returning to it. The antennae are doing exactly what a merger should do, triggering genuine, measurable, spatially distributed star formation. But the details of where and how keep complicating the simple story. The nuclei underperform. The overlap region overperforms relative to its gas density. The consumption clock ticks while the merger is not yet complete. The clusters forming now may outlive the merger itself, becoming the ancient globular clusters of whatever elliptical galaxy the antennae eventually produce. That last part stays with me. The star clusters forming in the antennae's overlap region today, packed with young blue stars, hot and luminous and brief in the way massive stars are brief, will, if they survive the dynamical turbulence of the ongoing merger, eventually become old, red, dense clusters orbiting a much larger and much quieter elliptical galaxy. What is being born in one of the universe's more active star-forming regions right now will eventually become one of the oldest-looking features of one of the most sterile types of galaxy known. The antennae show a merger working. They also show that even a merger that is working is more complicated, more spatially uneven, and more conditional than the standard picture suggested. What happens in the systems where the conditions are less favourable, where the gas fractions are lower, the geometry less aligned, the black holes more massive, is going to be considerably harder to characterise, and considerably more common. The early universe was wet, not in any literal sense. The word is astronomical shorthand, a taxonomy built on what galaxies carry inside them. But the galaxies forming in the first few billion years after the Big Bang were, by present standards, extraordinarily gas-rich. Their disks were thick with cold molecular hydrogen. Their star formation rates were high, sometimes dramatically so. The ratio of gas to stars, the gas fraction, was in many systems above 50%, meaning more than half the baryonic mass of the galaxy was not yet locked into stars. It was still available, still cold enough, still capable of collapse. The universe at cosmic noon, around 10 billion years ago, was full of galaxies with something to burn. That is not the universe we live in now. Gas fractions in present-day massive galaxies are low. Some are effectively zero. The cold molecular gas that once filled their disks has been converted into stars over billions of years of ongoing star formation, expelled by stellar winds and supernova feedback, heated by AGN activity, or simply never replenished after the cosmic supply of cold inflowing gas began to thin. The universe's inventory of raw star-forming material has been drawn down, not suddenly, not through any single dramatic event, but through the slow, sustained accumulation of star formation across cosmic time. What remains is distributed unevenly, abundant in low-mass late-type galaxies that have been forming stars slowly and conservatively for billions of years, and sparse to absent in the most massive systems which formed their stars early and have been largely quiet since. This matters for mergers in a way that is both obvious and easy to understate. The outcome of a galaxy merger depends, more than almost any other single variable, on what the merging galaxies are carrying when they arrive. Two gas-rich spirals colliding at redshift 2, each with gas fractions of 40 or 50%, each with thick, unstable, actively star-forming disks, are carrying enormous amounts of the compressible, collapse-ready fuel into the encounter. The tidal torques have something to work with. The shocks in the overlap region have dense clouds to compress. The nuclear inflows, when they develop, are feeding into regions that already have abundant molecular gas. The starburst has material. Two massive ellipticals colliding in the present-day universe are carrying almost none of that. Their gas fractions are a few percent at most, often less. Their disks, to the extent they have disks at all, are not cold molecular structures but warm, diffuse, dynamically hot systems of aging stars. There is no reservoir of collapse-ready gas for the tidal torques to funnel inward. There is no dense overlap region to shock into star formation. There is no nuclear accumulation building toward a starburst. The two systems meet, distort each other gravitationally, gradually merge their stellar populations, and produce a larger elliptical galaxy, more massive, rounder, older, without a single new star forming in the process. These are the dry mergers, and the fraction of mergers that are dry has been increasing since roughly the peak of cosmic star formation. The reason is structural. Massive galaxies, those with stellar masses above roughly 10 to the power of 10.5 solar masses, are predominantly gas-poor in the modern universe. They formed the bulk of their stars early, during and shortly after cosmic noon, and subsequent quenching mechanisms have kept them from replenishing their cold gas reservoirs. When two such galaxies are gravitationally bound to each other and eventually merge, the merger is between two systems that have already finished their star-forming lives. The encounter cannot restart what has been thoroughly stilled. There is something in this that functions like a one-way door, a galaxy that has been quenched, that has had its cold gas expelled or heated, or simply not replaced, does not easily recover its star-forming capacity from a merger alone. The merger adds stellar mass. It reorganizes the structure. It may briefly activate the central black hole if there is any residual gas to accrete. But the fundamental cold gas reservoir is gone, and without it, the tidal torques of the merger are torquing nothing that can collapse. The machinery of the encounter runs, but the output is structural rather than stellar. The wet-dry distinction also operates within what look like wet mergers, and this is where the picture gets more granular. Two galaxies can both carry cold gas and still produce a merger with surprisingly modest star formation if the gas fractions are not high enough, or if the gas has already been disturbed by a previous encounter, or if the geometry of the approach limits how efficiently angular momentum is removed. A merger with gas fractions of 10% is wet in a technical sense, but practically much closer to dry in its behavior than the label suggests. The threshold is not binary. It is a continuum, and where a given merger falls on that continuum depends on the specific gas content of each progenitor and on how that gas responds to the encounter's particular orbital geometry and timing. What the observations have shown, across large samples of merging pairs at different redshifts, is that only around 12% of major merging galaxies are genuinely starbursting. 12%. The rest show modest enhancements, flat rates, or in some cases suppression relative to non-merging controls. The majority of mergers, even among systems that nominally qualify as major mergers between comparable mass galaxies, do not produce starbursts. Many of them are simply not carrying enough gas to do so. The mergers that are gas-rich enough to starburst are increasingly concentrated at higher redshifts, in an earlier universe where gas fractions were higher and cold reservoirs more widespread. The fraction of dry mergers increases with the age of the universe. That sentence carries more weight than it might seem to on first hearing. It means that as cosmic time passes, as star formation slowly converts the universe's cold gas into stars and stellar feedback pushes what remains into warm or hot phases, the population of merging galaxies shifts toward encounters between systems that have less and less to offer each other in terms of new stellar ignition. The collisions become more frequent in one sense. Massive galaxies have had more time to accumulate companions, to fall into groups and clusters where encounters are more probable, and simultaneously less productive in terms of the one outcome that the word merger tends to evoke. By the time the universe reaches the age it currently has, roughly 13.5 billion years old, the mergers happening among the most massive galaxies are almost entirely dry. Two ancient ellipticals, each containing hundreds of billions of aging stars and almost no cold gas, drawn together by gravity into a single larger, ancient elliptical containing hundreds of billions of aging stars and almost no cold gas. The room was warm at some point. You can tell by the shape of things, the structure of the stellar populations, the age distributions, the chemical abundances frozen into the stars that formed during an earlier phase. But the warmth is gone. The gas that produced it was spent long before the two galaxies arrived at each other. What was needed to make something new was already gone when the collision began. The gas is there. That is the part that keeps pulling at the edges of the picture. In many post-merger systems, in galaxies that have been through the encounter, that carry the morphological signatures of a recent collision that should by every intuitive measure be sites of intense ongoing star formation. The molecular gas is present in substantial quantities. The cold reservoir has not been removed. It has not been expelled. CO observations, which trace molecular hydrogen indirectly and constitute the standard method for measuring cold gas content in external galaxies, consistently find that merging and recently merged systems often carry gas masses comparable to, or even somewhat elevated above those of non-merging galaxies at similar stellar masses. The gas is there. The stars are not forming from it at anything like the expected rate. Something is holding it. Turbulence is the answer most of the evidence points toward, and it is a strange answer because turbulence is also one of the mechanisms invoked to explain why mergers trigger star formation in the first place. The same physical process, the stirring and disruption of the interstellar medium by tidal forces, shocks, gas stream collisions, and stellar feedback, appears on both sides of the ledger. At certain scales and under certain conditions, turbulence compresses gas into star-forming clouds. At other scales and under other conditions, it prevents those clouds from forming or collapsing at all. The merger does not choose between these outcomes. It produces both, and which one dominates in a given region at a given time depends on a set of conditions that are genuinely difficult to disentangle from observations alone. The basic physics of why turbulence suppresses star formation involves something called the Jeans criterion. For a gas cloud to collapse under its own gravity, self-gravity has to overcome the internal pressure resisting compression. In a cold quiescent cloud, that pressure is thermal, determined by the temperature of the gas, which in cold molecular clouds is low enough that gravity wins fairly easily above a certain mass threshold. But pressure is not only thermal. Turbulent motion contributes what is sometimes called turbulent pressure, an effective resistance to compression arising from the disordered, high-velocity motions of the gas itself. If the gas in a cloud or across a region is moving turbulently at high velocities, that turbulent pressure can prevent gravitational collapse, even when the thermal pressure alone would not be sufficient to stop it. In pre-merger spiral galaxies, the gas velocity dispersion in the interstellar medium, the measure of how disordered and fast those internal motions are, sits at around 10 kilometers per second. Not zero, not perfectly still, but low enough that in dense regions the gravitational collapse of clouds proceeds relatively normally. The star formation is regulated, steady, following the relationship between gas surface density and star formation rate that normal disk galaxies obey. During a merger, the velocity dispersion in the interstellar medium climbs. Simulations and observations of interacting galaxy pairs consistently show values in the range of 30 to 40 kilometers per second, 3 to 4 times the pre-merger baseline. This is the turbulence the encounter generates, the tidal distortion, the shocks where gas streams from the two disks collide, the feedback from the star formation that the first-pass compression triggered, all contributing to a disordered, high-velocity gas field that is, in aggregate, considerably harder to collapse than the gas that existed in either galaxy before the interaction began. At 30 to 40 kilometers per second, the turbulent pressure in the interstellar medium is high enough to stabilize clouds against collapse that would otherwise be gravitationally unstable. Not everywhere, not all the time, the antennae show that star formation continues in the most strongly shocked regions despite the elevated turbulence. But across broad areas of the merging system, gas that looks dense enough to form stars on the basis of its column density alone is being held back by the disordered motions within it. The effective Jeans mass rises. Clouds that would have been above the collapse threshold in a quiescent disk are now below it, because the total pressure, thermal plus turbulent, has increased faster than the local density. This creates the situation that post-starburst observations keep finding and keep struggling to explain. The cold gas is present, CO detections confirm it, but the star formation rate is low, sometimes dramatically low relative to what the gas mass would predict under normal scaling relations. The gas is not forming stars efficiently. It is sitting in a state that is cold enough to be detected as molecular gas, distributed across the remnant in substantial quantities, but dynamically too disordered to collapse readily into the dense cores where stars actually form. There is something almost stubborn about it. The gas resists, not through any active mechanism, not through any self-awareness, but through the simple fact that the motions inside it are too energetic and too disordered for gravity to overcome. It is heavy and present and going nowhere useful. The merger that was supposed to compress it into a starburst has instead shaken it into a state of suspended inertia. The distinction between small-scale and large-scale turbulence matters here, and it is easy to lose. At small scales, within an individual giant molecular cloud, or at the boundary where two gas streams are colliding, turbulence can compress gas locally into dense filaments and cores. This is the mechanism behind the off-nuclear star formation seen in the Antennae's overlap region. Local, shock-driven compression producing discrete star-forming events in specific geometrically favourable locations. Real, measurable, but spatially limited. The turbulence at this scale is helping. At large scales, across the whole interstellar medium of the merging system, across the disk as a whole, the elevated velocity dispersion is doing the opposite. It is preventing the large-scale gravitational instabilities that would otherwise allow giant molecular clouds to assemble and collapse. It is keeping the gas in a diffuse, warmish, disordered phase from which individual star-forming events can only sporadically emerge. The global star formation efficiency, the fraction of available gas converted to stars per unit time, drops. Is this the dominant mechanism in post-merger quenching? Probably not the only one. The black holes are doing things. The morphology of the remnant is doing things. The CGM is involved. But turbulence as a suppressor, as a mechanism that leaves the gas present and cold but functionally inert, is increasingly supported by the molecular gas observations that keep finding gas-rich post-merger systems with unexpectedly low star formation rates. What the merger gave, the merger also partly took away. The disturbance that compressed some gas into the first new stars also stirred the rest into a state that resists further collapse. The same energy, deposited into the interstellar medium through tidal forces and shocks and feedback, appears on both sides of the star formation ledger simultaneously. Whether the compression winds or the stirring winds depends on local conditions that vary across the system, across the merger sequence, across the range of galaxy masses and gas fractions and orbital geometries involved. There is no single answer. There is only the specific gas in the specific merger at the specific moment, and what the turbulence happens to be doing to it right then, and the gas is still there. That much keeps being true. At the centre of nearly every massive galaxy sits a supermassive black hole. Not hypothetically, not as an inference from indirect evidence alone, though the evidence is indirect in most cases, but as a feature of galactic structure so consistent, so tightly correlated with the properties of the surrounding stellar population, that it is now treated as a standard component of the galaxy rather than an exceptional one. Millions of solar masses at minimum, billions at the high end, sitting in the nucleus, mostly quiet, mostly doing very little in the periods between significant accretion events. The Milky Way's central black hole, Sagittarius A star, currently accretes at a rate so low it barely registers as active by AGN standards. It is there. It is massive. It is not at the moment doing much. That changes during a merger. Not immediately. Not at the first pass, not during the long interval between encounters when the galaxies separate and the tidal tails persist, and the disturbed disks slowly process what the encounter has left behind. The black hole responds to what arrives at the nucleus, and what arrives at the nucleus depends on the gas dynamics of the whole system, on whether the tidal torques are efficiently stripping angular momentum from the gas, on whether the inflows that develop during the encounter are delivering material to the central region at a rate high enough to significantly increase the accretion. Angular momentum is the obstacle. Gas in the galactic disk is rotating. It has been rotating for a long time, and that rotation is what keeps it in stable circular orbits rather than falling inward under the galaxy's gravitational potential. To move from the disk toward the nucleus, to close the distance between, say, a few kiloparsecs and the subparsec scales where the black hole's gravity dominates, the gas has to lose most of that angular momentum. This is not a small requirement. The angular momentum per unit mass of gas in the outer disk compared to gas at the edge of the black hole's gravitational sphere of influence differs by orders of magnitude. Something has to remove it, and remove it efficiently for any substantial quantity of gas to actually reach the nucleus. In quiescent galaxies, this happens slowly and in small amounts. Viscosity in the gas, instabilities in the disk, minor perturbations from passing satellites. These processes deliver a trickle of low angular momentum gas to the nucleus, enough to keep the black hole accreting at a low level, enough to explain why even nominally inactive galactic nuclei have some measurable nuclear emission. But a trickle is a trickle. The black hole stays in its quiet state. During a merger, the tidal forces generate non-axisymmetric structures, bars, spiral distortions, elongated gaseous features that are qualitatively different from the minor perturbations of a quiescent disk. The gravitational torques from these structures act on the gas throughout the disk, not just in the outer regions. Gas that was in stable circular orbits finds itself in a potential field that is no longer symmetric around the galactic center. The orbits it was following no longer close on themselves. Radial motions develop, and gas that develops radial motion, that begins falling inward rather than orbiting, has in effect started losing angular momentum to the stellar and dark matter distribution around it through gravitational torques. This is not instantaneous. The inflow develops over the course of the encounter, building as the tidal distortions deepen, accelerating during the close approaches when the non-axisymmetric perturbations are strongest. Gas accumulates in the central kiloparsec, then in the central few hundred parsecs, then closer still. The density in the nuclear region rises, and when the nuclear gas density rises past a threshold that depends on the black hole mass and the available gas supply, the accretion rate onto the black hole increases, not by a small factor, but by factors of 2 to 5 compared to the pre-merger state, according to what the major cosmological simulations consistently show. The AGN luminosity climbs with the accretion rate. The black hole is not more massive yet. That takes time, and the timescale for significant black hole mass growth is longer than the timescale of the starburst, but it is brighter. It is processing more material per unit time, and the energy released by that accretion, radiated from the hot, compact region around the black hole, is real and substantial. At the peak, in the most gas-rich major mergers, the AGN luminosity can approach or exceed the luminosity of a quasar. What makes this complicated, and this is the part that took the field some time to work through, is that the peak AGN luminosity and the peak star formation rate tend to occur at nearly the same moment. Both are being driven by the same underlying event, the accumulation of gas in the nuclear region during and immediately after coalescence. The star formation peaks because gas density has risen to the point where gravitational collapse is rapid and widespread. The AGN peaks because gas with low angular momentum is reaching the nucleus and being accreted. Same gas reservoir, same physical driver. 2 different outputs happening simultaneously. This simultaneity was initially taken as evidence of a causal connection. The merger triggers both the starburst and the AGN, and therefore mergers link starburst to AGN activity in a straightforward way. The picture was tidier than the reality. What the more detailed simulation showed, and what observations have increasingly confirmed, is that while mergers do elevate both star formation and black hole accretion, the fraction of merging galaxies hosting clearly AGN-dominated nuclei at any given moment is not as high as the simple picture predicted. And conversely, most AGN in the universe are not found in recent merger remnants. The connection exists, it is real, but it is not the dominant pathway in either direction. The more important question for the fate of star formation in the merger remnant is not whether the black hole brightens during the merger. It almost certainly does. The question is what the brightened black hole does to the gas around it. And here the picture is less settled than it might appear. The AGN can accrete for roughly 100 million years after the starburst has effectively ended, sustained by the small quantities of low angular momentum gas that continue trickling inward even after the main reservoir has been consumed or expelled. During that interval, the energy output from the AGN is being deposited into the surrounding gas. How efficiently that energy couples to the gas, whether it heats it, expels it, or simply passes through it with minimal effect, determines whether the black hole's awakening becomes consequential for the galaxy's long-term star formation capacity, or merely a brief luminous episode that fades without structural consequence. The black hole, having drawn in what the merger sent its way, is now doing something with that energy. What it does with it is the mechanism that either closes the story or extends it considerably. That mechanism has a name. It has two modes. And the difference between those modes is, in the end, the difference between a galaxy that slowly recovers from star formation after the merger and one that never does. The word feedback is doing a lot of work in galaxy evolution, and it is worth being honest about how imprecise it sounds for something that turns out to matter so much. In everyday use, feedback is a loop, information returning to its source, adjusting the output. In astrophysics, it means something more specific and more physical, the process by which energy released by an accreting black hole is deposited into the surrounding gas in a way that affects that gas's ability to cool, condense, and form stars. The black hole releases energy. The gas receives it. What the gas does with that energy, whether it heats up and stays hot, whether it gets pushed outward, whether it manages to cool back down and re-enter the star formation cycle, or whether it is permanently removed from that cycle, depends on how the energy is delivered. And how the energy is delivered turns out to be everything. There are two broad modes of AGN feedback that matter for this story. They go by several names in the literature: quasar mode and radio mode, radiative mode and kinetic mode, high accretion and low accretion, but the clearest distinction, the one that maps most directly to what the gas actually experiences, is thermal versus kinetic. Thermal feedback deposits energy as heat. Kinetic feedback deposits energy as momentum. Both involve energy transfer from the AGN to the surrounding gas. The similarity ends there. Thermal feedback is what happens when a rapidly accreting black hole, one operating near its Eddington limit, accreting at a high fraction of the maximum rate its mass allows, produces intense radiation. That radiation interacts with surrounding gas, photoionizing it, heating it. The gas temperature rises, pressure builds. In principle, a hot enough gas cloud will expand and disperse, temporarily suppressing star formation in its immediate vicinity by raising the thermal genes toward mass, the minimum mass above which gravitational collapse can proceed, and by creating a hot pressurized environment in which cool, dense, star-forming clouds struggle to persist. In practice, thermal feedback has a problem. Hot gas cools. The cooling rate of ionized gas depends on its density. Denser gas cools faster through more frequent collisions between particles. And in the dense nuclear regions of a galaxy where thermal feedback is strongest, the gas that gets heated can radiate away that heat and cool back to star-forming temperatures on timescales that are short relative to the AGN episode. The energy was deposited. The gas heated briefly. The gas cooled again. The star formation was suppressed for a time, then resumed. The AGN produced an effect, but not a lasting one. This is the core limitation of thermal feedback as a quenching mechanism. It can regulate star formation, certainly. It can hold it down, slow it, prevent it from running away during the high accretion phase when the GN is brightest. But it cannot permanently remove the cold gas reservoir. It heats what is present, does not eject it. When the AGN dims, when the accretion rate drops and the radiation field weakens, the gas that was heated but not expelled gradually cools and settles back. The galaxy is not quenched. It is paused. Simulations that implement only thermal feedback, or that implement thermal feedback as the dominant mode, consistently overproduce massive galaxies relative to what is observed. Without a mechanism that permanently removes or prevents the recooling of gas, the models allow too much gas to cycle back into star formation after a GN episode's end. The galaxy keeps forming stars when it should have stopped. The red sequence, the observed population of massive, quiescent, non-star-forming galaxies, cannot be reproduced at the right abundance without something more effective than thermal heating alone. Kinetic feedback is more effective, not more energetic necessarily. The total energy budget of kinetic feedback can be lower than that of thermal feedback during a quasar phase AGN, but more effective in terms of what it actually does to the gas. Kinetic feedback occurs when the accreting black hole drives mechanical outflows, rather than primarily radiating energy into the surrounding medium. At lower accretion rates, when the black hole is accreting at a small fraction of its Eddington limit, which is typically the state it settles into after the initial high accretion merger phase has passed, the energy is not released primarily as radiation, but as directed mechanical output. Jets of plasma moving at relativistic or near-relativistic speeds, wide-angle winds carrying momentum outward through the galaxy. The energy couples to the surrounding gas not by heating it in place but by pushing it. The distinction matters because momentum cannot be radiated away. When kinetic energy is deposited into a gas cloud, it accelerates the gas. The gas moves. If the momentum injection is sufficient, if the outflow velocity exceeds the escape velocity of the galaxy at that radius, the gas does not just move, it leaves. It is ejected from the disk, from the inner halo, carried outward into the circumgalactic medium and beyond. This is ejective feedback, and it does something that thermal feedback alone cannot. It physically removes the fuel. But ejective feedback is only half of what kinetic mode GN activity accomplishes, and arguably the less important half over long time scales. The other consequence is preventive feedback, the effect of kinetic outflows on the circumgalactic medium itself. The circumgalactic medium is the reservoir of diffuse multi-phase gas that surrounds a galaxy out to its virial radius. It is the source from which the galaxy replenishes its cold gas supply, through cooling flows, gas in the CGM radiating away its thermal energy, cooling to the temperatures where it becomes molecular, and raining back down onto the disk. This cooling flow is how a galaxy that has consumed some of its cold gas can, under normal circumstances, recover. The CGM acts as a buffer, a long-term reserve from which the disk can draw. Kinetic AGN feedback disrupts this process. The outflows driven by the low accretion rate black hole propagate outward through the disk and into the CGM, depositing momentum and energy into the halo gas. The halo gas heats. Its cooling time, the time it takes to radiate away its thermal energy and cool to star-forming temperatures, increases. In sufficiently massive halos, where the AGN is energetic enough and the halo gas density is low enough that the heating rate from the outflow exceeds the cooling rate of the gas, the CGM reaches a quasi-stable hot state. It is not cooling efficiently. The cooling flow that would replenish the disk's cold gas reservoir has been suppressed. This is preventive feedback. The galaxy is not just losing its current cold gas supply to outflows, it is being cut off from the source that would replace it. Illustris TNG, which currently reproduces the observed properties of massive quiescent galaxies better than earlier simulations, implements kinetic AGN feedback as the dominant quenching mechanism. The results are instructive. Galaxies in Illustris TNG quench when their black holes become massive enough, roughly above 10 to the 8.2 solar masses, and the kinetic feedback from those black holes acts in two ways that match the observations reasonably well. First, it ejects gas from the inner galaxy directly, reducing the cold gas available for star formation. Second, it heats the CGM, extending cooling times and preventing the cold gas reservoir from being replenished by inflow from the halo. The quenching, when it occurs, is not instantaneous. It is cumulative. The black hole drives outflows. The CGM slowly heats. The cooling rate drops. The disk's cold gas is gradually consumed by whatever star formation continues. and the replenishment that would normally offset that consumption is no longer arriving efficiently. Star formation slows, not because something violent happened, but because the supply chain was disrupted quietly and persistently over a period that can extend to hundreds of millions of years. Whether kinetic feedback alone fully accounts for the observed quenching of massive galaxies is not settled. The gap between simulations and observations, the 30 to 60 times excess quenching found in observed post-mergers compared to the 2 to 11 times found in even the best simulations, suggests that something is still being underestimated or missed. The kinetic feedback mode is the right mechanism in the right direction. The magnitude of its effect and how sensitively it depends on physical conditions that current simulations cannot fully resolve remains genuinely open. The gas that left the galaxy is now in the CGM or beyond it. Some of it will eventually cool, fall back, and rejoin the disk in a galactic fountain, Moort. The most massive systems with the most energetic outflows will not. It will sit in the hot halo indefinitely, held there by continued low-level AGN activity, and by the virial temperature of the halo itself. It was cold gas once. It was close to forming stars. It is not anymore, and the question of whether it ever returns is less a matter of time than of what the black hole decides, which is not a decision at all, just physics running forward under conditions that increasingly favour the halo staying hot. After the merger has run its course, after the two nuclei have finally coalesced, after the tidal tails have dispersed or fallen back, after the AGN has cycled through its brightest phase and dimmed again, what remains is a shape, not metaphorically, literally, a distribution of stellar mass in three-dimensional space, and that distribution has consequences that are physical rather than aesthetic. The shape of the remnant is not just a record of what happened during the merger. It is an active participant in what happens next. The merger between two disk galaxies produces, in most cases that involve comparable masses and sufficient interaction time, a galaxy that is no longer disk-dominated. The ordered, rotating, flattened structure that each progenitor carried into the encounter has been disrupted. The angular momentum that organized both disks into their pre-merger configurations has been redistributed, some of it into the tidal tails and dispersed into the surrounding space, some of it transferred between the stellar and gas components during the interaction, some of it simply scrambled by the repeated gravitational perturbations of multiple close passes. What emerges from coalescence tends to be rounder, more dispersion-dominated, more like an ellipsoid than a disk. The stars that were once moving in organized circular orbits are now moving in a much more disordered mix of orbits, supporting a structure that is held up by the random kinetic energy of stellar motions rather than by the coherent rotation of a spinning disk. This is the morphological transformation, and for a long time it was understood primarily as a structural outcome of the merger, an interesting consequence, but not itself a mechanism with further implications. The stars move differently now. The galaxy looked different. That was recorded and moved past. What Martig and colleagues showed in 2009 through cosmological simulations using zoom-in techniques that could follow individual galaxy evolution in detail was that the morphological transformation is not just a consequence, it is a cause. The change in shape actively suppresses star formation through a mechanism that operates entirely independently of gas removal, independently of AGN feedback, independently of virial shock heating, a mechanism that works even if none of those other processes are operating at all. The mechanism runs through disk instability analysis, and it is worth following carefully. In a disk galaxy, star formation does not occur uniformly across the gas. It occurs where the gas becomes gravitationally unstable, where local overdensities grow rather than disperse, where a perturbation in the gas surface density can amplify itself into a collapsing cloud, rather than being smoothed out by the disk's rotation and internal pressure. The criterion that determines whether a perturbation grows or disperses is the Tumor Q parameter, which balances the stabilizing effects of rotation and pressure against the destabilizing effect of the gas's self-gravity. Low Q means the disk is gravitationally unstable. Perturbations grow, clouds form, stars eventually do too. High Q means the disk is stable. Perturbations are suppressed before they can amplify into anything collapsible. In a normal disk galaxy, the stellar mass distribution is also disk-like, and its contribution to the overall gravitational potential is organized and relatively predictable. But when the merger transforms that stellar distribution into a spheroid, a much more extended, three-dimensional, non-rotating distribution of stellar mass, the potential that the gas disk sits inside changes fundamentally. The spheroidal stellar component does not contribute the kind of ordered gravitational support that a stellar disk would. Instead, it provides a smooth, extended background potential that the gas disk has to orbit within, and the background potential suppresses the growth of gravitational instabilities in the gas. The intuition is this: a gas disk embedded in a spheroidal stellar potential experiences a kind of gravitational smoothing. The perturbations that would normally grow into collapsing clouds, the small overdensities that in a disk galaxy can run away into giant molecular clouds, are suppressed because the spheroidal potential does not cooperate with the growth of local overdensities the way a disk potential does. The effective Q of the gas disk rises. The disk becomes stable against fragmentation. Star formation is suppressed not because the gas has been removed or heated, but because the structural environment in which it sits no longer permits the instabilities that star formation requires, and the gas keeps arriving. This is the part that the simulation showed explicitly, and that is, in a quiet way, one of the strange results in this area. The Martig simulations tracked galaxies through the morphological quenching phase, and found that during this period, which can extend for billions of years, cold gas continues to accrete onto the galaxy from the surrounding halo and from minor mergers. The gas fraction in the disk is not zero. The halo is not empty. Gas is still coming in, still cooling, still settling onto the disk in a continuous low-level inflow. But it is not forming stars efficiently. It sits in the disk in a cold state, unable to fragment into star-forming clouds because the spheroidal stellar potential stabilizes it against the instabilities that would allow it to do so. The galaxy is going red. Its colors are shifting. The blue light from young massive stars fading as those stars age and die and are not replaced. The integrated stellar population reddening toward the infrared over hundreds of millions of years, while the disk still contains gas and the halo is still supplying it. The reddening is not caused by gas depletion. It is caused by the inability of the present gas to form new stars, which is caused by the shape of the stellar distribution that the merger produced. One person joining moves the number. That one move matters more than it looks, and if you have been thinking about it, the Patreon link is in the description. Geometry as a quenching mechanism is strange to hold in mind. Quenching is usually framed in terms of removal, something taking the gas away, or heating, something raising the gas temperature above the threshold for collapse. Morphological quenching requires neither. The gas is cold, the gas is present. The gas is simply sitting inside a structure that will not let it do what cold gas in a disk would normally do, which has become something else. It is worth being precise about what this mechanism does and does not explain. Morphological quenching stabilizes the disk against fragmentation, but it does not explain how the gas that continues to accrete is eventually removed, or why massive elliptical galaxies in the local universe are not simply gas-rich quiescent galaxies full of cold inert disk material. Something else, a GN feedback, virial shock heating, or their combination, is presumably responsible for eventually depleting or heating even the gas that morphological quenching has stilled. The mechanism is not complete on its own. It is a contributor, a suppressor, an additional weight on the gas that was already being weighed down by other processes. What it establishes is that the shape of the galaxy after the merger is not neutral. It is doing something. The spheroid that formed from two disrupted disks is not just a record of what those disks were. It is an active physical environment that changes what the remaining gas can become. The Remnant's geometry is not a memory of the merger. It is one of the merger's ongoing consequences, still working, still suppressing, long after everything else about the collision has faded. Beyond the disk, beyond the spiral arms and the molecular clouds and the star-forming regions and the tidal debris of the merger, there is more gas, a great deal more gas distributed in a diffuse multi-phase envelope that extends from the outer edge of the stellar disk outward to the virial radius of the dark matter halo, a distance that, for a massive galaxy, can reach hundreds of kiloparsecs. This is the circumgalactic medium. It is not the galaxy in the way the disk is the galaxy, but it is not separate from the galaxy either. It is the atmosphere of the galaxy, the medium through which the galaxy exchanges material with the intergalactic environment, the reservoir from which the disk draws when its own cold gas supply runs low. It is also, during a merger, doing several things simultaneously and in different directions. The CGM is not a single substance. At any given moment it contains gas at a wide range of temperatures, from cold filaments at temperatures around 10,000 Kelvin to warm gas at 10 to the 5 Kelvin to hot, diffuse plasma at temperatures above 10 to the 6 Kelvin. These phases are not neatly separated in space. They are interleaved, mixed at boundaries where thermal instabilities drive cool gas to condense out of hot surroundings, where galactic winds push warm enriched gas outward into cooler regions, where infalling intergalactic material enters the halo and begins to interact with what is already there. The CGM is busy in the way that complicated systems are busy. Not obviously, not loudly, but continuously and in multiple directions at once. What matters for the merger story is what the CGM contributes to the galaxy's fuel supply. In a galaxy that is actively forming stars, the cold gas in the disk is being consumed. Star formation converts molecular gas into stars. Supernovae return some of that material to the interstellar medium in heated form, and the net effect over time is that the cold gas reservoir in the disk depletes if it is not replenished. Replenishment comes from two directions, from minor mergers and satellite accretion, which can deliver cold gas directly to the disk, and from the CGM through a process of cooling and inflow. Gas in the CGM that has sufficient density in the denser filaments in the cooler regions can radiate away its thermal energy, drop in temperature, and eventually cool to the point where it becomes molecular and settles onto the disk in a slow, continuous rain of new cold gas. This cooling inflow is the mechanism by which a galaxy sustains itself between episodes of direct gas accretion. It is not dramatic. It does not arrive in a rush. It is a gradual, sustained replenishment that offsets the ongoing depletion from star formation and keeps the cold gas fraction in the disk from declining to zero. During the merger, the CGM becomes a more active participant than this quiet replenishment role suggests. Simulations that include a proper CGM, cosmological zoom-in simulations that model the gas in the halo, as well as the gas in the disk, show something that idealized closed-box merger models missed entirely. At the time of coalescence, between 27 and 51% of the star-forming gas in the merger is not gas that was originally in either galactic disk. It is gas that was in the CGM before the merger began and has been accreted into the star-forming region during the encounter. The merger draws on the halo reservoir. The tidal distortions of the merger and the increased accretion rates during the encounter pull CGM gas inward, adding it to the cold gas available for star formation at exactly the moment when the disk gas is most compressed and most actively forming stars. This has a direct consequence for how quenching is understood. Idealized merger simulations, which initialize all the gas in the two galaxy disks and ignore the surrounding halo, overestimate how thoroughly a merger depletes the cold gas supply, because they do not account for the CGM replenishment happening in parallel with the depletion. Real mergers, embedded in their full cosmological CGM context, have access to a gas reservoir that extends far beyond the disk boundaries and that reservoir is contributing to star formation throughout the encounter. The merger cannot simply consume its way to quenching if the halo keeps sending gas down. For quenching to be sustained, but for the galaxy to actually stop forming stars rather than experience a temporary suppression followed by recovery as the CGM recools and replenishes the disk, something has to happen to the CGM itself. This is where the AGN kinetic feedback from Chapter 9 extends its reach. The outflows driven by the low accretion rate AGN, the kinetic mode, the mechanical jets and winds that propagate outward from the nucleus, do not stop at the edge of the disk. They propagate into the CGM. As they move outward through the halo gas, they deposit momentum and energy into the diffuse medium around them. The halo gas heats. In regions where the outflow energy density is high relative to the local gas density, which tends to be true in the inner and middle halo of a massive galaxy, with an active AGN, the heating rate can exceed the cooling rate of the gas. The cooling time, which is the timescale on which a parcel of gas radiates away its thermal energy and drops to lower temperatures, stretches. In the most massive halos, with the most energetic AGN outflows, the cooling time in the inner CGM can be pushed above the halodynamical time, the time scale on which gas would otherwise be expected to flow inward and replenish the disk. When the cooling time exceeds the dynamical time, the CGM is not cooling efficiently. The gas that was slowly raining down onto the disk is no longer raining. It is sitting in the halo, hot and diffuse, moving but not cooling, present but not accessible. The replenishment flow has been suppressed, not eliminated perhaps, not at every radius, not permanently in every circumstance, but reduced below the rate that would sustain ongoing star formation in the disk. The disk is now consuming its remaining cold gas without replacement arriving at the rate it needs. Star formation continues, but it is drawing on a diminishing reserve. The rate declines, the galaxy reddens. The stellar population ages without new additions from the young, blue, massive end. I keep returning to what this actually means spatially. The galaxy still has a halo. The gas is still out there, not gone, not ejected to infinity in most cases, just held at temperatures and densities where it cannot efficiently cool and fall. The galaxy is surrounded by its own gas and cannot use it. The AGN feedback has not removed the reservoir. It has changed the conditions inside the reservoir so that the reservoir no longer functions as one. Whether the CGM eventually recovers, whether after the AGN dims and the kinetic outflows weaken, the halo gas gradually cools again and restarts the replenishment flow, depends on the mass of the halo and the mass of the black hole and the ongoing balance between heating and cooling at each radius. In lower mass systems, recovery is possible. The AGN episode ends, the halo cools, the disk gets new gas, some star formation resumes. In the most massive systems, the halo mass itself contributes a virial temperature high enough that even without the AGN running continuously, the gas stays too warm to cool efficiently. The AGN heated it past a threshold it cannot easily return from. The last source of fuel has become unreachable, not because it is gone, because everything around it has changed. The number is 30 or 60, depending on how the sample is defined, how the post-Starburst classification is applied, how stringently the post-merger galaxies are identified, but somewhere in that range, the observational result is consistent and has been replicated across different surveys and different methodological approaches. Post-merger galaxies, galaxies that have recently completed coalescence, identified through morphological signatures of recent interaction in imaging data from the Union survey, are between 30 and 60 times more likely to host a recently and rapidly quenched stellar population than a matched sample of non-merging galaxies. 30 to 60 times. That is not a subtle enhancement. That is a signal strong enough that it is difficult to attribute to selection effects or classification ambiguity. Mergers are doing something to star formation, or rather, to the cessation of star formation, at a rate that substantially exceeds what happens in galaxies without recent merger histories. The observation is, within its methodology, robust. Now the simulations, Illustris TNG, currently among the most sophisticated and well-validated cosmological hydrodynamical simulations available, finds a factor of approximately 2. Post-merger galaxies in Illustris TNG quench at roughly twice the rate of matched non-merging controls within 500 million years of coalescence. 2 against 30 to 60 Eagle, a different simulation with different subgrid physics prescriptions, finds a factor of 11, better than Illustris TNG by nearly an order of magnitude, still below the observed range by a factor of 3 or more. And Illustris, the predecessor to Illustris TNG, finds essentially no excess at all. Its post-merger quenching rate is statistically indistinguishable from its control, which means Illustris is not even capturing the direction of the effect, let alone its magnitude. 3 simulations, 3 different answers, none of them matching the observations. The spread among the simulations is itself informative. It means the result is sensitive to modelling choices, which means the modelling choices matter enormously and are not yet understood well enough to converge on the right answer. The gap is not a rounding error. The gap between a factor of 2 and a factor of 30 to 60 is a structural disagreement between the models and the data, and it deserves to be taken seriously as such. Not as a crisis for the field, the simulations reproduce many other properties of the galaxy population quite well, but as a specific, localized failure to capture whatever physical mechanism is responsible for the observed strength of merger-driven quenching. What are the simulations doing and where might they be falling short? Each of the 3 simulations implements AGN feedback, the mechanism most theorists believe is responsible for merger-driven quenching, but implements it differently. Illustris TNG uses a kinetic feedback mode at low accretion rates that injects momentum into surrounding gas particles, suppressing cooling and driving outflows, with a transition to thermal feedback at high accretion rates. Eagle uses thermal AGN feedback as its primary mode, with the feedback energy injected stochastically to avoid numerical overcooling. Illustris uses a 2-mode scheme as well, but with different coupling efficiencies and a bubble injection mechanism for the radio mode that proves, in hindsight, to be too gentle to reproduce observed quenching rates. The differences in feedback implementation produce the differences in quenching rates, which tells you directly that the quenching in these simulations is sensitive to how the feedback is modelled, not just whether feedback is present. The issue is resolution. Not resolution in the technical sense alone, though resolution matters, but the resolution of the physical scales on which the relevant processes operate. A GN feedback in reality operates on scales ranging from the sub-parsec accretion disk, where the outflow is initially launched, to the hundreds of kiloparsec scale of the CGM, where the cumulative effect of heating determines whether the cooling flow is suppressed. Current cosmological simulations cannot resolve the sub-parsec scales. They cannot follow the actual launching of the outflow from the vicinity of the black hole. Instead, they use subgrid prescriptions, parameterized models that describe the net effect of the unresolved physics at the resolution scale of the simulation, which is typically on the order of a kiloparsec or larger. The feedback energy is deposited at this scale, with coupling efficiencies that are calibrated to reproduce global galaxy properties but are not derived from first principles. This means the simulations are essentially guessing, in a principled and carefully calibrated way, how much of the AGN's energy actually couples to the surrounding gas and on what timescale. If the real coupling is more efficient than the subgrid prescriptions assume, if the actual outflows launched by the AGN carry more momentum per unit energy than the models implement, or if they couple to the gas at smaller radii where the gas density is higher and the effect more consequential, then the simulations will consistently underestimate the quenching rate. They will get the direction right. They will show some excess quenching in post-mergers, but they will fall below the observed magnitude, because the mechanism they are implementing is a diluted version of the real thing. There is also the question of what the observations are actually measuring. The observational sample of post-mergers is identified morphologically through the presence of tidal features disturbed morphologies, double nuclei, and this identification is imperfect. Some genuine post-mergers will be missed because their merger signatures have faded. Some non-post mergers will be included because of morphological disturbances from other causes. The Post-Starburst classification used to identify the rapidly quenched galaxies within the post-merger sample also carries its own selection effects. It is possible, though careful analyses suggest unlikely, that some fraction of the 30 to 60 times excess is an artifact of how the samples were assembled. But even allowing for methodological uncertainty on the observational side, the gap between 2 and 60 is too large to close through sample corrections. Something is genuinely different between what the simulations are producing and what the universe is doing. One candidate for the missing physics is the detailed structure of the ISM during the merger. The cold, dense, clumpy, turbulent medium that real AGN outflows have to propagate through, and that is not resolved in any current cosmological simulation. Outflows moving through a clumpy medium interact with it differently than outflows moving through a smooth medium at the same mean density. The dense clumps can be accelerated and entrained more efficiently, carrying cold gas out of the galaxy in a way that smooth medium models do not reproduce. If this clumpy entrainment is significantly more effective at removing cold gas than current prescriptions assume, the quenching rate in simulations with realistic ISM structure would be higher, potentially much higher. Another candidate is the timing of the feedback relative to the merger sequence. If the AGN responds to the merger more quickly or more strongly than current models capture, if there is a phase early in the coalescence when the accretion rate spikes sharply, and the feedback is both more intense and better coupled than the subgrid prescription produces, then the simulations are missing a burst of quenching relevant feedback at exactly the moment when the merger most strongly predisposes the galaxy toward quenching. The honest answer is that the gap exists, it is large, and it is telling something. What precisely it is telling, which missing physics, which underestimated coupling, which unresolved scale, is not yet agreed upon. The simulations are not wrong in a way that invalidates what they show. They are incomplete in a way that matters for this specific question, which is the one question this story depends on most directly. The number is still 30 to 60. The best simulation is still at 2. The distance between them is where the physics is hiding. Not everything that prevents a galaxy from forming stars arrives from the merger. Some of it was already built into the structure of the halo before the two galaxies ever began to close the distance between them, written into the physics of how gas falls through gravitational potential wells, how it heats when it meets resistance, and how the balance between heating and cooling shifts as the total mass of the system crosses certain thresholds. The merger can accelerate a galaxy toward quiescence. It can trigger the AGN activity that heats the circumgalactic medium. It can exhaust the cold gas reservoir through a starburst or drive turbulence that prevents efficient star formation. But for the most massive galaxies in the universe, there is a separate mechanism operating underneath all of that, one that does not require a merger to function, that was going to suppress star formation eventually regardless, and that makes the massive end of the galaxy population structurally different from everything below it. That mechanism involves the dark matter halo, and it begins far from the galaxy itself. Gas in the intergalactic medium is cold by cosmological standards, temperatures around 10,000 Kelvin or below, thin, diffuse, moving slowly through the large-scale structure of the universe along filaments and through voids. When this gas encounters a dark matter halo, when it begins to fall inward along the halo's gravitational potential, it accelerates. Gravitational potential energy converts to kinetic energy as the gas falls, and when infalling gas moving at supersonic velocities meets denser gas already present in the halo, or reaches the region where the halo's gravitational influence is strong enough to be called a boundary, something happens to all that kinetic energy. It converts to heat through a shock. The shock is not a surface in any literal sense. It is the transition region, a zone where the infalling material decelerates rapidly and its ordered kinetic energy is thermalized, converted into the disordered thermal motion of the gas particles. the temperature of the gas jumps. On the downstream side of the shock, the gas is no longer cold intergalactic material moving at supersonic infall velocities. It is hot, quasi-static halo gas sitting at temperatures that reflect the depth of the gravitational potential well it has fallen into for a sufficiently massive halo. Temperatures in the range of 10 to the 6th to 10 to the 7th Kelvin. At these temperatures, the gas does not cool quickly. This is the critical point. The cooling time of a gas, the time it takes to radiate away its thermal energy through collisional processes and drop to lower temperatures, depends on both the temperature and the density of the gas. In the dense central regions of a galaxy, gas can cool quickly even when hot, because the density is high enough that collisions between particles happen frequently and the cooling rate per unit volume is substantial. But in the diffuse outer halo, where the gas density is low, the cooling time is long, and for gas at temperatures above roughly 1,000,000 Kelvin in a low-density halo environment, the cooling time can exceed the dynamical time of the halo, the timescale on which gas would be expected to flow inward and replenish the galaxy's disk. When the cooling time exceeds the dynamical time, the hot halo gas does not cool and fall, it sits, it accumulates, heated by each new shock from each new infalling parcel of intergalactic gas, maintained in its hot quasi-static state by the continuous energy input from the virial shock. The galaxy at the center of the halo is no longer receiving the cold infall it needs to sustain star formation. The supply has not been cut by a merger. It has been cut by the size of the halo. The critical halo mass at which this transition occurs, the mass above which a stable virial shock can be maintained and the hot halo gas cannot efficiently cool, sits at roughly 10 to the 12th solar masses. Below this threshold, cooling dominates over shock heating. Infalling gas radiates away its thermal energy quickly, drops to low temperatures, and reaches the disk as cold gas available for star formation. Above this threshold, a stable hot corona forms around the galaxy. The cold infall that sustained star formation at lower masses is replaced by a diffuse hot atmosphere that is structurally unable to feed the disk efficiently. The threshold is not perfectly sharp. The transition from cold mode to hot mode accretion is gradual, and there are conditions under which cold filamentary streams can penetrate the hot halo and deliver cold gas to the disk even above the critical mass, particularly at high redshifts when the halo gas is denser and the filaments more robust. But the broad transition is real, it is theoretically predicted, and it corresponds closely to the observed stellar mass above which galaxies are predominantly quiescent in the local universe. The halo mass threshold and the galaxy color bimodality sit at the same scale, which is not a coincidence. What this means for the merger story is specific. A galaxy that has grown its halo above 10 to the 12th solar masses, which is not unusual for massive ellipticals, whose halos can reach 10 to the 13 or even 10 to the 14 solar masses, has already lost access to the cold infall that would sustain ongoing star formation, independently of whether a merger has occurred. The merger, if it happens, is arriving after the halo has already crossed the threshold. The virial shock was already operating. The hot corona was already suppressing the cooling flow. The AGN feedback from the merger adds to the suppression, may push the cooling time higher, may heat the inner CGM more thoroughly. But it is not the only mechanism at work, and in the most massive systems it may not even be the dominant one. The galaxy was, in some sense, already going to stop forming stars. The merger participates in that process. It does not originate it. There is something slightly uncomfortable about this. If you have been following the story from the beginning as a story about mergers causing quenching, the halo mass threshold complicates the causality. The most massive galaxies, the ones whose mergers are most often invoked as examples of merger-driven quenching, are also the ones whose halos most thoroughly suppress cold infall independently of the merger. Separating the contribution of the merger from the contribution of the halo mass is not straightforward observationally, because the same galaxies that undergo major mergers tend to be the same galaxies that live in massive halos. The virial shock does not care about the merger. It responds to the halo mass. And above a certain mass, it was always going to heat what falls in, always going to extend the cooling time past the point of utility, always going to leave the disk without its supply. The merger arrives into conditions that were already tilting towards silence. What the merger does is, sometimes under the right conditions, with the right black hole mass and the right gas fraction and the right orbital geometry, tip what was already tilting. The question that has been building across the last several chapters is one that the merger story tends to sidestep, and it is worth stating plainly before trying to answer it. When a galaxy merges and then quenches, when the coalescence is followed within a few 100 million years by a sharp decline in star formation, by the exhaustion of the cold gas supply, by the transition from blue and active to red and still, so what exactly did the merger do? Did it cause the quenching? Did it accelerate something that was going to happen anyway? Did it simply arrive at a moment when the conditions were already in place? And what we are calling merger-driven quenching is in large part the quenching of galaxies that were already heading toward quiescence, observed at the moment a merger happened to be completing. This is not a comfortable question because it cuts against the narrative structure that makes the merger story feel coherent. Mergers are events. Events cause things, the starburst follows, the AGN activates, the feedback drives, the quenching results. The causal chain is satisfying in the way that clear sequences are satisfying. But the evidence from the simulations, and increasingly from the observations themselves, suggests that the chain is not as clean as it looks, and that the most important variable in whether a merger produces quenching is not something the merger introduces, but something the galaxies carried into the encounter long before it began. The pre-existing gas fraction is where the evidence is clearest. In the major cosmological simulations, Eagle, Illustris, TNG, the post-merger galaxies that quench rapidly are not a random sample of the post-merger population. They are the subset that arrived at coalescence with low gas fractions already in place. In both simulations, more than 80% of the post-mergers that quench within 500 million years of coalescence had gas fractions at or below 20% at the time of the merger, and the post-mergers that quench most rapidly, those that drop below the star-forming main sequence most sharply and most permanently, tend to be the ones that had gas fractions below 5%. The merger encountered a galaxy that was already running low on fuel. The merger consumed or expelled what remained. What looks like merger-driven quenching is, in substantial part, the rapid completion of a depletion process that had been underway for some time before the two galaxies made contact. The black hole mass tells a similar story. Quenching in Illustris TNG requires the central black hole to exceed roughly 10 to the 8.2 solar masses. Below this threshold, even post-merger galaxies with elevated AGN. Accretion rates do not quench within the relevant timescale. That black hole mass was not produced by the merger. It was accumulated over the entire prior history of the galaxy through previous accretion events, previous minor mergers, previous episodes of AGN activity. The merger that triggers the final quenching encountered a black hole that was already massive enough to do the job. A merger arriving into a galaxy with a lower mass black hole, one that has not yet accumulated the mass needed to drive effective kinetic feedback, does not produce the same outcome, even if the gas fractions and orbital geometries are otherwise identical. The halo mass adds a third layer to the same picture. As Chapter 13 established, halos above roughly 10 to the 12th solar masses are already suppressing cold infall through virial shock heating, independently of any merger activity. The massive galaxies most likely to undergo major mergers, because they live in dense environments, in groups and clusters where close encounters are more probable, are also the galaxies whose halos have most thoroughly crossed this threshold. The merger is arriving into a system where the external fuel supply was already being cut off by a structural feature of the halo that predates the merger by billions of years in some cases. 3 pre-existing conditions, each one independently associated with quenching, each one present in the galaxies that quench post-merger before the merger occurred. The merger encounters all 3 simultaneously, low gas fraction, massive black hole, hot halo, and the result looks like the merger quenched the galaxy. Whether it did, or whether it found a galaxy already so close to the quenching threshold that almost anything would have finished the job, is a distinction the post-merger observations cannot easily make. There is a version of this that understates the merger's role, and it is worth being careful not to fall into it. The merger does something. The excess quenching in the post-merger galaxies 30 to 60 times above the control rate in observations is real, and it is not fully explained by selection effects. Galaxies with the same pre-merger gas fractions and the same black hole masses do not quench at the same rate if they are not undergoing a merger. The merger is contributing something beyond what the pre-existing conditions alone would produce. The most careful reading of the evidence is not that the merger is irrelevant, but that it is insufficient, that it requires a particular pre-existing state to produce the outcome, and that it is the combination of the merger and the predisposition that drives quenching rather than either alone. The merger in this framing is an occasion. It is the event that brings together the mechanisms, the final angular momentum loss that lets the black hole accrete at its highest rate, the last compression of an already thin gas reservoir, the final starburst that consumes what remains before the AGN feedback cuts off replenishment and concentrates them into a brief interval where their combined effect is sufficient to push the galaxy across the quenching threshold. Without the pre-existing state, the same merger would produce a starburst and then a recovery, as the CGM recools and refuels the disk. With the pre-existing state, the same merger produces a starburst and then silence, because there is nothing left in the CGM to recool, nothing in the disk to sustain what the starburst began, no remaining gas fraction to absorb the feedback and continue. What the collision found was a galaxy already arriving at its ending. The merger did not write that ending. It met it partway through. This reframing does not make the merger less interesting. If anything, it makes it more so, because it means the merger is acting as a kind of accelerant and a finalizer simultaneously, compressing what might have been a slow, drawn-out decline into a rapid transition that leaves a cleaner observational signature. The post-starburst galaxies that Ellison and colleagues identified in the post-merger sample are galaxies where the decline happened fast enough to leave a spectral imprint of the starburst that preceded it, fast enough to show up as a discrete population rather than a smooth continuum. The merger made the ending abrupt, the predisposition made the ending inevitable. How you weigh those two contributions against each other depends on what you think causation means in a system where no variable acts alone. Everything discussed so far has assumed that the feedback affecting a galaxy comes from within it. The AGN at the center of a merging galaxy drives outflows that heat the ISM and CGM of that same galaxy. The turbulence generated by the tidal interaction disrupts the molecular clouds of that same galaxy. The morphological transformation stabilizes the disk of that same galaxy against collapse. The mechanisms are internal, originating inside the system they affect, driven by processes happening within the boundaries of the galaxy being quenched. That assumption is not wrong for most of what happens in most mergers, but it is incomplete, and the way it is incomplete is strange enough to deserve its own chapter. In November 2025, a paper submitted to RxIV described a system at redshift 1.61, roughly 10 billion years ago, near the peak of cosmic star formation, that offered something the field had discussed theoretically but never directly observed. Clear evidence of one galaxy's AGN suppressing star formation in a physically separate companion galaxy, before the two had coalesced. The mechanism was named the dragon effect by the authors, and the naming has a specific reason. The AGN outflow from one galaxy reaches outward, across the narrowing space between two systems still in the process of merging, and acts on the cold gas of the neighbour, not the galaxy the black hole lives in, but the one next to it. The system consists of two massive galaxies at a projected separation of approximately 8 kiloparsecs. The host galaxy, the one containing the active AGN, identified through X-ray emission, shows signatures of an ongoing starburst. Its star formation rate is elevated. Its gas is being compressed by the interaction. It is doing what a gas-rich merging galaxy in favourable conditions does. The companion, at 8 kiloparsecs away, is doing something different. Its star formation has recently and rapidly declined. Its stellar population shows spectral signatures consistent with a post-starburst phase, the characteristic signature of a galaxy that experienced an elevated star formation rate in the recent past, and then had that star formation shut down quickly. The starburst in the companion happened, and then stopped. The AGN in the companion is not detected. The black hole in the companion is not currently active at a level that would explain the quenching through internal feedback. What is present at 8 kiloparsecs is the outflow from the host galaxy's AGN. The geometry matters here. 8 kiloparsecs is not a large distance by galactic standards. It is well within the region where AGN-driven outflows are known to propagate. Kinetic outflows driven by actively accreting black holes can extend to tens of kiloparsecs from the nucleus, carrying momentum and energy into the surrounding medium as they go. An outflow launched from the host galaxy's AGN, directed toward or passing through the companion's position, would deposit energy and momentum into the companion's cold gas reservoir. That gas, which was participating in the star formation triggered by the first pass of the merger, would be heated, pressurized, and potentially expelled from the companion's disk before the companion's own internal processes had time to consume or preserve it. The result would look exactly like what is observed. A companion galaxy with a recent starburst now quenched, with no clear internal quenching mechanism operating at a level sufficient to explain the shutdown. The quenching came from outside. The dragon effect is not the same as the internal AGN feedback discussed in previous chapters. It is geometrically distinct in a way that changes how it needs to be modelled and how it needs to be searched for observationally. Internal AGN. Feedback operates symmetrically outward from the nucleus of the galaxy being quenched. External AGN feedback, one galaxy's black hole affecting another, operates directionally from one nucleus toward a neighbour, and the strength of its effect depends on the separation between the two systems, the direction of the outflow relative to the companion's position, and the density of the companion's gas at the point where the outflow arrives. This directionality is part of why the dragon effect was not identified earlier. Simulations of galaxy mergers have historically focused on the internal evolution of each galaxy, what the AGN does to its own ISM and CGM, without tracking in detail what the outflow does when it propagates far enough to reach the companion. And observational studies of quenching in merging pairs have generally assumed that the quenching of each galaxy can be explained by that galaxy's own internal properties and history. The possibility that one galaxy in a pair might be quenching the other through external feedback requires looking at the two systems jointly, tracking the spatial direction of the outflow from the active galaxy and comparing it to the position and state of the companion. The Z equals 1.61 system is, as of the paper's submission, the first case where this connection has been made directly and with sufficient supporting evidence to propose it as the explanation rather than a coincidence. It may not remain the only case for long. The authors note that the conditions required for the dragon effect, two massive galaxies in a close pair, one with an active AGN at sufficient luminosity, the other carrying a cold gas reservoir that the outflow can reach, are not exotic. They are the conditions that characterize a substantial fraction of major mergers at cosmic noon, when AGN activity and merger rates were both near their peak. If the dragon effect operates in a meaningful fraction of close pairs at redshift 1 to 3, then the standard accounting of quenching mechanisms in mergers is missing a contribution. Not from the black hole of the galaxy being quenched, but from the black hole of its neighbour. The feedback budget of a merger is not the sum of two independent internal feedbacks. It is something more coupled, more geometrically contingent, more dependent on the specific spatial relationship between the two systems at the moment of peak AGN activity. How common the dragon effect is, whether it is a rare alignment of conditions or a systematic contributor to quenching in merging pairs, is not yet known. The physics that would govern its frequency involves variables that are difficult to constrain observationally. The AGN luminosity as a function of merger stage, the solid angle subtended by the outflow, the gas density of the companion at the relevant separation. Future multiphase hydrodynamic simulations, the authors suggest, could quantify its dependence on these parameters. But the simulations would first need to resolve the outflow at sufficient detail to track what it does between the two nuclei. One galaxy's black hole acting on another galaxy's gas before the two galaxies have merged. The feedback does not wait for coalescence. It reaches. How far it reaches and how often is a question that is now at least being asked in the right direction. Two elliptical galaxies are falling toward each other. This has been happening for some time, long enough that the approach is committed, the outcome decided by gravity and angular momentum and the geometry of their encounter, not by any remaining contingency. They are not gas-rich. They have not been gas-rich for a long time. Their star formation histories peaked billions of years before this moment, during an earlier cosmic epoch when their progenitors were disk galaxies with abundant cold reservoirs and active stellar nurseries along their spiral arms. That epoch ended. The gas was consumed, expelled, heated beyond the cooling threshold, denied replenishment by halos that had grown massive enough to maintain hot coronae indefinitely. The galaxies reddened. The blue light from young massive stars faded as the last generation of high-mass stars aged off the main sequence and nothing formed to replace them. What remained were aging stellar populations, growing redder and dimmer in infrared wavelengths as the stellar mass settled into lower mass, longer-lived stars that would persist for billions of years without drama. Now those remnants are approaching each other, and the approach, unlike the wet mergers described in earlier chapters, carries almost no consequence in terms of new physical processes being triggered. The tidal forces are real, the gravitational interaction is real, the distortion of each system's stellar distribution by the differential pull of the other is happening exactly as it happens in gas-rich encounters, but the tidal forces have nothing particularly interesting to act on. In a wet merger, the tidal torques strip angular momentum from cold molecular gas, driving it inward, compressing it, feeding nuclear starbursts and AGN accretion events. The gas responds to the tidal field because gas has pressure, because gas can shock, because gas can lose angular momentum through gravitational torques in ways that produce inflows toward the center. In a dry merger, the material being torqued is stars. Stars behave like collisionless particles during a gravitational encounter. They follow the gravitational potential without interacting with each other directly, without shocking, without compressing into higher density configurations that could trigger collapse. The tidal tails that form in a dry merger are stellar tails, diffuse and faint, streams of stars drawn outward by the differential gravitational pull. They are structurally similar to the tidal tails of a wet merger. They contain no cold gas. They are not forming stars. They are simply stars that have been displaced from their previous orbits and are now tracing long, slow arcs through the space around the merging system. The two nuclei are approaching. In a wet merger, this final approach triggers the most intense phase of star formation and AGN activity. The cold gas that has been accumulating in the nuclear regions of both galaxies over the course of the interaction is finally compressed together. The starburst peaks, the black holes accrete. In a dry merger, the two nuclei approach and then merge into a single, more massive nucleus. And the main consequence is dynamical. The stars that were orbiting each nucleus are now orbiting a combined mass. Their orbital energies are redistributed. The new nucleus is more massive, with a deeper gravitational potential, and the stellar distribution around it reorganizes accordingly, becoming rounder, more extended, supported by the increased velocity dispersion of its stellar population, rather than by any rotational structure that the original galaxies may have retained. The black holes at the centers of both galaxies are there. In a wet merger, The inflow of cold gas toward the nucleus at coalescence can spike the accretion rate significantly, brightening the AGN by factors of 2 to 5. In a dry merger, what reaches the nucleus is not cold gas. There may be residual warm gas in the system, diffuse ionized, not particularly amenable to rapid accretion, but the supply is thin. The black hole accretion rate during a dry merger shows little enhancement above the already low quiescent rate of both progenitors. The AGN does not brighten significantly. The feedback that in wet systems heats the CGM and suppresses cooling flows is not being driven here in any meaningful new way. The halo is already hot. The black holes are already in their low accretion radio mode. The merger finds everything already in the state that AGN feedback would produce, because it was there before the merger arrived. What the dry merger does produce is mass. The stellar mass of the remnant is the sum of the stellar masses of the two progenitors, minus a small fraction lost to tidal stripping into the surrounding environment. This is not trivial. Dry mergers are believed to be responsible for a significant fraction of the size and mass growth of the most massive elliptical galaxies since redshift 1, the growth that cannot be attributed to star formation, because there is none, but which is clearly real in the observed evolution of the size-mass relation for massive galaxies. The remnant is larger than either progenitor, not because new stars formed, but because old stars from two separate systems have been added together into a single, more extended distribution. The size growth is real and happens in a specific way. When two comparable mass ellipticals merge, the stars from each system add their orbital energies to the combined system. The remnant is not just more massive, it is more extended, because the orbital energy deposited during the merger inflates the stellar distribution outward. The effective radius of the remnant, the radius containing half its total stellar mass, is larger than that of either progenitor by a factor that depends on the mass ratio and the orbital parameters of the encounter. This size growth without star formation is one of the mechanisms invoked to explain why massive elliptical galaxies at the present day are significantly larger than ellipticals of comparable stellar mass observed at high redshift, which formed their stellar mass earlier when the universe was denser and more compact. Velocity dispersion grows too. The stars in the remnant are moving faster on average than the stars in either progenitor, because the deeper gravitational potential of the combined system requires higher velocities to maintain stable orbits. The central velocity dispersion, the measure of how fast stars near the nucleus are moving, is a quantity tightly correlated with black hole mass in observed ellipticals, and it rises as the remnant assembles. The black hole mass and the stellar velocity dispersion track each other across the dry merger sequence, not because the black hole is growing through accretion, but because the stellar system around it is growing through the addition of new stars from the companion. Somewhere in the outer halo of the remnant, the stars that were once in the tidal tails are settling into low-density streams and shells, faint, diffuse structures that trace the geometry of the encounter and persist for billions of years as the most visible evidence that two separate systems were once here. They are old stars moving on new orbits. The galaxy they are now part of is larger and older than either of the galaxies they came from. Nothing new is forming. The stars that exist in the remnant were made in another era, in conditions that no longer exist and will not return. They will age. They will die in the slow way that low-mass stars die, gradually, over time scales longer than the current age of the universe in some cases. The remnant will grow dimmer, not dramatically, not suddenly, but in the persistent, almost geological way that things change, when no renewal is arriving. Two galaxies approached. One larger, older, quieter thing remains. If you plot every galaxy you can measure against two axes, how bright it is and what colour it is, a pattern emerges that is robust enough to have survived decades of increasingly precise data. The distribution is not random, it is not uniform, it clusters. At one end, a broad, relatively scattered population of galaxies that are blue, emitting more light at shorter wavelengths, a signature of ongoing star formation, of young, massive stars still burning hot before their brief lives end. At the other end, a tighter, more concentrated population of galaxies that are red. Their light shifted toward longer wavelengths, a signature of an older stellar population, of a history in which star formation has stilled, and the surviving stars are the long-lived, lower-mass ones that age slowly toward infrared dimness. Between those two populations, a region that is noticeably less crowded than either side. That middle region is the Green Valley. The name is informal and slightly misleading. There is no literal green colour involved. The word refers to the intermediate position in the colour distribution, but it has become standard enough to use without apology. And the question that the Green Valley poses is not difficult to state, though it takes some care to answer. Why is the middle of this distribution sparsely populated? Why do galaxies pile up on either side, in the blue cloud and on the red sequence, but not in between? The most straightforward interpretation is that galaxies do not stay in the Green Valley long. If the transition from blue to red was slow, if galaxies spent billions of years gradually decreasing their star formation rates, fading gently from blue to green to red across cosmic time, the Green Valley would be as populated as the regions on either side, because at any given moment a large fraction of galaxies would be mid-crossing. The fact that it is not well populated implies that the crossing is fast. Galaxies enter the Green Valley and exit it on timescales short enough that only a small fraction are caught in transit at any moment. Fast, in this context, means relative to the age of the universe. Early type galaxies, the ellipticals and lenticulars that end up on the red sequence, appear to quench on timescales as short as 250 million years in some cases. The colour transition from the blue edge of the Green Valley to the red sequence for these systems takes less than 1 billion years, and often considerably less. Late-type galaxies are slower. Their star formation can decline more gradually over several billion years, while they remain technically in the Green Valley. A slower crossing driven by gentler processes like gas starvation, or bar-driven secular evolution, rather than the sharp feedback-driven quenching associated with major mergers and AGN activity. The epoch matters too, and this is where the Green Valley becomes genuinely useful as a window into how quenching has changed over cosmic time. At intermediate redshifts, around Z equals 0.7 or so, when the universe was roughly half its current age, the typical quenching timescale inferred from Green Valley populations is shorter than in the local universe. Galaxies at this epoch cross the Green Valley in less than 500 million years on average. In the local universe, the same crossing takes 1 to 2 billion years for the bulk of the population. The speed of the transition has been declining as the universe ages, which is another way of saying that quenching was more abrupt and more efficient at earlier cosmic times, and has become more gradual as the universe has grown older and the conditions that drove rapid quenching have become less prevalent. This epoch dependence is not surprising given everything established in earlier chapters. Cosmic noon, around redshift 2, was the period of peak gas fractions, peak merger rates, peak AGN activity, and peak star formation simultaneously. Galaxies quenching at that epoch were doing so in an environment where cold gas was abundant enough to fuel intense starbursts. AGN accretion rates were high enough to drive strong kinetic feedback, and CGM replenishment was being cut off efficiently by the combination of AGN heating and virial shocks in rapidly growing massive halos. The quenching, when it happened fast. The starburst consumed the gas quickly. The AGN feedback heated the CGM thoroughly. The halo mass crossed the virial shock threshold while the galaxy was still young. The Green Valley crossing at cosmic noon was a sprint. In the present-day universe, the galaxies still transitioning are doing so in a very different environment. The available cold gas is lower. The AGN episodes are less intense on average. The processes driving quenching are more likely to be slow. Environmental strangulation in groups and clusters, gradual gas depletion without efficient replenishment, secular morphological transformation. than the sharp feedback-driven transitions of the earlier universe. The crossing is a walk rather than a sprint, and the green valley is correspondingly more populated at its late type end in the local universe than it was at higher redshifts. There is a subtlety in the green valley's sparseness that is easy to overlook, and it concerns what sparse actually means observationally. The green valley is not empty. It contains galaxies, some in the process of declining star formation, some that have temporarily elevated their star formation through a minor merger or gas accretion event and are briefly bluer than their equilibrium colour, some that are genuinely intermediate in their stellar populations and evolutionary state. The sparseness is relative, a statement about the ratio of green valley to blue cloud and red sequence populations, not about the absolute absence of transitioning galaxies. And there is evidence from some analyses that the observed sparseness is partly a consequence of dust correction. Galaxies with ongoing but dust-obscured star formation can appear redder than their intrinsic colour and be misclassified as green valley or red sequence galaxies when they are actually still in the blue cloud. But even allowing for these complications, the basic signal is robust. Galaxies do not linger in the middle for long. Something is moving them through. Using colour as a proxy for star formation history, which is what the colour magnitude diagram implicitly does, means using colour as a proxy for time elapsed since quenching began. A galaxy that is slightly green has been declining for less time than one that is nearly red, other things being equal. The width of the green valley in colour space, combined with the crossing timescale inferred from how many galaxies are in it relative to the flanking populations, gives you an estimate of how long the transition takes. And that crossing timescale, few 100 million years for fast-quenching early types, few billion years for slower-quenching late types, is itself a constraint on the mechanism. A quenching mechanism that operates on a 100 million year timescale, like the sharp AGN, feedback following a major merger starburst, produces a fast green valley crossing. A mechanism that operates on a billion-year timescale, like the gradual starvation of a satellite galaxy being slowly stripped of its CGM as it orbits in a cluster, produces a slow crossing. The distribution of crossing speeds in the observed green valley population is therefore a distribution of mechanism signatures, with different quenching pathways visible as different speeds of transit through the same intermediate region. The colour magnitude diagram does not tell you what quenched a galaxy, but it tells you how fast the quenching was, and from the speed you can start to narrow down what kind of process could have been responsible. Some galaxies crossed in a breath, others are still crossing. The diagram records all of it without preference in the accumulated light of their aging stars. 10 billion years ago, the universe was doing something it has not done since and will not do again. Not in the sense of a unique event, not a collision or an explosion, or a discrete moment that can be pinpointed to a specific date, but in the sense of a sustained condition, a period of several billion years during which the circumstances for star formation, galaxy growth, black hole accretion, and the mergers that connect all three were simultaneously at their most favourable. Astronomers call it cosmic noon. The name implies a midpoint, which is roughly accurate. It sits at roughly redshift 2, about 10 billion years in the past, when the universe was around 3.5 billion years old, and the cosmic star formation rate density had reached its peak value before beginning the long, gradual decline that continues to the present day. Cosmic noon was not a quieter or more orderly time than now. It was considerably less so. The galaxies forming and merging at redshift 2 were different from the galaxies merging today in ways that are not merely quantitative. Their gas fractions were dramatically higher. Many systems carrying cold molecular gas at 30, 40, 50% of their total baryonic mass in Bibamans, compared to the few percent typical of massive galaxies in the present universe. Their star formation rates were correspondingly higher, not just in absolute terms but per unit stellar mass. The specific star formation rate, the rate at which a galaxy was adding new stars relative to its existing stellar population was elevated by factors of 10 or more compared to galaxies of similar mass today. The disks of these galaxies were thick, clumpy, gravitationally unstable structures that fragmented into massive star-forming clumps in ways that the thin, settled disks of the modern universe do not. The interstellar medium was more turbulent, more dynamic, more thoroughly engaged in the process of converting gas into stars than anything in the local universe except the most extreme starburst galaxies. The merger rate was higher too, not because gravity worked differently, but because the universe was smaller and denser at redshift 2. The moving volume was the same as today, but the physical distances between galaxies were compressed by the factor of 1 plus redshift, meaning galaxies were physically closer to their neighbours and gravitational encounters more frequent. The fraction of massive galaxies undergoing major mergers at any given moment was higher than the few percent observed today. The fraction undergoing minor mergers, accretion of smaller satellite galaxies, was higher still, and the AGN were running. The AGN fraction peaks near redshift 2 as well, which is not a coincidence. Abundant cold gas, frequent interactions funneling low angular momentum material toward galactic nuclei, rapidly growing black holes accreting at high fractions of their Eddington limits. The conditions that produced luminous AGN were concentrated at this epoch. The quasar population, the most luminous AGN in the universe, peaks at cosmic noon and declines on either side. At redshift 2, there were more quasars per unit volume than at any other time in cosmic history. Many of the most massive black holes in the universe today, the billion solar mass objects sitting quietly at the centres of the largest elliptical galaxies, assembled most of their mass during this epoch, fed by the high accretion rates that the abundant cold gas supply and frequent merger-driven inflows made possible. All three peaks, star formation, merger rate, AGN activity, coincide at roughly the same cosmic epoch. This is not accidental, they are connected. The cold gas abundance drives the star formation. The same cold gas, funneled inward by merger-driven tidal torques, feeds the AGN. The AGN feedback, in turn, drives the quenching that terminates the star formation and begins the transition of massive galaxies from the blue cloud to the red sequence. The three peaks are aspects of the same underlying condition: a universe with abundant cold gas, rapidly assembling massive structures, and the physical processes that consume and redistribute that gas running at their highest rate simultaneously. Mergers at cosmic noon were, for all these reasons, capable of producing outcomes that mergers in the present universe typically cannot. A major merger between two gas-rich spirals at redshift 2 arrived into a system where both progenitors might carry gas fractions of 40% or more. The tidal torques of the encounter acted on an enormous reservoir of cold compressible material. The nuclear inflows were substantial, the starburst intense, the black hole growth rapid. The feedback from that growth, the kinetic outflows from a black hole accreting at near Eddington rates for extended periods, was energetic enough to heat the CGM of the merge system efficiently, extending cooling times above the dynamical timescale and cutting off the external gas supply. The combination of starburst consumption, AGN ejection, and CGM heating could drive a galaxy from gas-rich and actively star-forming to quiescent within a few 100 million years. The Green Valley crossing was fast because the mechanisms doing the crossing were running at their highest intensities. That is not the universe mergers happening today. The galaxies merging in the present universe are, on average, less gas-rich than their redshift 2 counterparts. The cold gas supply in the universe as a whole has been drawn down by 10 billion years of star formation. Stars have been forming continuously since the first galaxies assembled, and each generation of stars converts some cold gas into stellar mass. Some of it returned to the ISM in heated form by supernovae and stellar winds. Some of it locked permanently into stellar remnants. The net effect across cosmic time is a gradual depletion of the universe's cold gas inventory that mirrors the decline in the cosmic star formation rate. The two are the same phenomenon measured in different units. Mergers today are more likely to be dry or gas-poor than mergers at cosmic noon, because the universe today has less cold gas per galaxy than it did at redshift 2. The starburst, when it occurs, is fueled by a smaller reservoir and produces a less intense event. The AGN, fed by thinner inflow, accretes at a lower fraction of its Eddington limit and drives weaker kinetic feedback. The CGM in lower mass halos may not be heated efficiently enough to prevent recooling and reaccretion. The quenching, when it occurs, may be slower, less complete, more susceptible to reversal by subsequent gas accretion events. The universe's capacity for star formation is in long-term structural decline, not because the physics has changed. Gravity still works, gas still collapses under the right conditions, stars still form when molecular clouds exceed the gene's mass. But because the raw material is running low. The cold gas that was abundant at cosmic noon has been spent slowly and continuously across the 10 billion years since. What remains is distributed in lower mass, lower density systems and galaxies that are forming stars at modest rates from modest reservoirs, and will continue to do so for a very long time, but at rates that are small fractions of what the universe was doing at its peak. The most massive galaxies are largely done. Their star formation peaked at or before cosmic noon, was quenched by the mechanisms this story has traced, and has not substantially restarted. They are aging, growing slowly through dry mergers that add stellar mass without new stars, becoming larger and dimmer and older as the universe continues to expand and cool around them. Somewhere in the afternoon light of a universe past its most active period, the mergers continue, quieter now, less consequential in terms of new stellar birth. Still gravitationally inevitable, still structurally transformative, still producing the largest objects in the observable universe through the patient accumulation of mass upon mass, just not making much that is new. The gas is there. This has come up before, but here it is the whole problem rather than a detail within a larger one. In post-starburst galaxies, systems that carry spectral signatures indicating a recent intense burst of star formation followed by a sharp decline in star formation rate, the kind of systems that appear in elevated numbers in post-merger samples. The molecular gas has not been removed. CO observations, which trace molecular hydrogen through the emission of carbon monoxide and constitute the standard method for measuring cold molecular gas mass in external galaxies, find substantial cold gas reservoirs in a significant fraction of post-starburst systems. Not traces, not residual wisps. Molecular gas masses that in some cases approach or match those of normal star-forming galaxies at comparable stellar masses. The gas is there, the star formation is not. The star formation rate in these systems is, by the spectral classification that identifies them as post-starbursts, dramatically below the galactic main sequence. They have stepped off the star-forming main sequence, the tight relationship between stellar mass and star formation rate that characterizes normal star-forming galaxies, and have done so recently and rapidly, while retaining cold gas reservoirs that should, under normal scaling relations, be producing stars at substantial rates. The standard Kennicutt-Schmidt relation, which relates gas surface density to star formation rate surface density across a wide range of galaxy types, predicts star formation rates for these gas masses that are orders of magnitude above what is observed. The gas is not behaving the way gas at this mass and temperature normally behaves. Something is holding it. Not physically, not a wall, not a force that can be pointed to and named in the way all can be named. Something more subtle and more structural. The gas is cold, it is molecular. It is there in the quantities that should be sufficient, but it is not collapsing into stars efficiently because the conditions inside the gas and around it are not the conditions that star formation requires. The first contributor is turbulence, which Chapter 7 introduced in the context of the ongoing merger. In post-starburst galaxies, which are by definition recent merger remnants in many cases, The elevated ISM velocity dispersions generated by the merger have not yet fully dissipated. Turbulent energy decays, but not instantly. The time scale for turbulent dissipation in a galactic ISM is on the order of a crossing time, the time it takes a turbulent eddy to traverse the region it occupies, which can be tens to hundreds of millions of years for large-scale galactic turbulence. A galaxy observed a few 100 million years after its merger-driven starburst may still carry ISM velocity dispersions well above the quiescent baseline, enough to prevent the gravitational fragmentation of gas into the dense, compact cores where stars actually form. The turbulent pressure in the post-starburst ISM is suppressing what the gas would otherwise do. The gas has the mass, it has the temperature. It does not have the internal quiescence that collapse requires. But turbulence alone does not account for the full picture, because turbulence dissipates. Given enough time, the ISM would settle. The velocity dispersions would drop back toward the pre-merger baseline. The dense gas fraction would recover. Star formation would resume. Some post-starburst galaxies do show evidence of gradual recovery, a slow reactivation of star formation as the turbulence dissipates and the gas begins to fragment again. The paradox would resolve itself if the turbulence were the only mechanism. The molecular gas observations suggest it is not. CO spectral line energy distributions, measurements of how the molecular gas is distributed across different excitation states, from the lower G transitions that trace cool diffuse gas to the higher J. Transitions that trace warmer, denser gas, consistently show that the molecular gas in post-starburst galaxies is predominantly in a low excitation state. It is cold and diffuse rather than warm and dense. The fraction of the total molecular gas mass that is in the dense high excitation phase, the phase from which stars actually form, is low. Not zero, but significantly below the dense gas fractions observed in actively star-forming galaxies or in starburst systems. This is the dense gas fraction problem, and it is distinct from the turbulence problem. Even in regions where the turbulence has partially dissipated, even in regions where the bulk velocity dispersion has settled toward lower values, the gas is not efficiently assembling into the dense molecular cloud cores that are the direct precursors of star formation. It remains diffuse. It remains cold in the CO sense, detectable present, but not concentrated into the configurations that collapse. Morphological quenching introduced in Chapter 10 adds a third layer. The merger that produced the post-starburst population also transformed the morphology of the remnant from disk-dominated to spheroid-dominated. The spheroidal stellar potential stabilizes the gas disk against the large-scale gravitational instabilities that would otherwise allow giant molecular clouds to assemble. The gas that is there, cold, present, detectable, is sitting inside a structure that suppresses the very fragmentation it needs to undergo to become stars. The Tumri Q parameter of the disk is elevated by the spheroidal background potential, keeping the gas in a stable configuration that is, in the language of disk instability theory, resistant to the growth of the overdensities that star formation requires. 3 mechanisms, all operating simultaneously, none of them individually sufficient to explain the full suppression. Together, elevated turbulent pressure, low dense gas fraction, morphological stabilization, they produce a gas reservoir that is physically present, spectroscopically detectable, and functionally unable to do what gas is supposed to do. The post-starburst galaxy carries its fuel without being able to burn it. Not because the fuel is wet, not because it has been treated with something that prevents ignition, but because the environment in which it sits, the turbulent, spheroid-stabilized, dynamically disturbed remnant of a major merger, does not permit the organizational steps that combustion requires. Gas has to assemble into dense cores before it can collapse. Dense cores have to be shielded from the surrounding radiation field and supported against tidal disruption long enough for gravity to win. In the post-starburst environment, the steps that would normally lead from diffuse molecular gas to dense core to protostar to star are being interrupted at multiple points simultaneously. What this reveals about star formation more broadly is something the post-starburst population makes unusually legible. The conversion of gas into stars is not just a function of how much gas is present, it is a function of what state that gas is in, what physical environment it occupies, and whether the conditions for each step in the organizational hierarchy, from diffuse ISM to molecular cloud to dense core to protostellar collapse, are simultaneously satisfied. Break any step in that hierarchy and the gas stalls. It does not form stars. It waits, in whatever state the environment imposes on it, for conditions to change. In some post-starburst galaxies, conditions eventually do change. The turbulence dissipates slowly, the AGN dims and the kinetic feedback weakens. Minor gas accretion from the CGM or a small satellite adds new material that has not been through the starburst. A fraction of the cold gas finds its way into dense enough configurations that a few new stellar nurseries begin. The galaxy does not fully recover, does not return to main sequence star formation at the rates it sustained before the merger, but it is not entirely stilled either. In others, the conditions that suppress star formation are themselves maintained by ongoing process. The CGM remains too hot to replenish the disk efficiently. The morphology remains spheroid-dominated. The turbulent energy is topped up by continued low-level AGN activity, or by the accretion of satellite galaxies. The gas reservoir slowly depletes, consumed in the rare collapse events that do occur, gradually photoionized by the aging stellar population, eventually accreted onto the black hole in small amounts, without ever producing star formation at a rate that would show up as blue light in the galaxy's integrated colour. The gas was there. For a while it stayed there. Then, without particular announcement, it was not. What remains after everything is a shape in space, not a small one. The massive elliptical galaxies that emerge from the merger histories this story has traced are among the largest gravitationally bound stellar systems in the observable universe, some of them containing trillions of stars, extending across hundreds of kiloparsecs at their outermost edges, embedded in dark matter halos that reach further still. They are not diminished by what happened to them. In terms of raw stellar mass, they are the most impressive objects of their kind. The dry mergers that followed the initial wet merger or mergers that quenched them added stellar mass without adding new stars, growing the remnant outward through the accumulation of old stellar populations from consumed companions. The size is real. The mass is real. What is absent is something that does not have mass, something that cannot be weighed or imaged directly, but whose absence is legible in the light the remnant emits. The light from a massive elliptical galaxy is old. Not metaphorically old, physically old, in the sense that the photons arriving at a detector from these systems were produced predominantly by stars that formed billions of years ago, during the starburst phases of the mergers, or in the gas-rich disk phases of the progenitor galaxies before the mergers began. The youngest stars in a fully quenched massive elliptical are not particularly young. They may be several billion years old, formed during the last residual star formation episode before quenching completed, and they have long since evolved off the main sequence. What remains on the main sequence are the lower mass stars, the K and M dwarfs, and the slightly more massive G dwarfs, burning hydrogen slowly and producing light that is yellow and orange and, at the population level, integrates to a colour that sits firmly on the red sequence of the colour magnitude diagram. There are no O stars, no B stars. The massive hot blue stars that produce the ultraviolet and blue optical light characteristic of actively star-forming galaxies have all died quickly, as massive stars do, on timescales of millions of years, and nothing has replaced them. The blue light is gone. The ultraviolet emission that would indicate ongoing ionization of hydrogen gas by young stellar radiation is absent. The H2 regions, the glowing clouds of ionized hydrogen surrounding young stellar clusters, visible as bright nebulae in star-forming galaxies, are not present because there are no young stellar clusters to ionize them. The interstellar medium of the remnant does not glow in the ways that indicate life in the stellar sense. It is not dark, not optically empty. There is still starlight, still the diffuse emission from the aging stellar population, but it is the light of something that is not making anything new. The interstellar medium itself is sparse, not the cold, turbulent, clumpy molecular medium of a gas-rich spiral galaxy, not the network of giant molecular clouds that in star-forming galaxies fills the disk with dense, cold, gravitationally active structures. What remains is a thin, warm, ionized or weakly ionized medium, a residual gas component that is not cold enough to be molecular in most regions, not dense enough to fragment, not organized into any structure that could collapse. Some of this gas is material returned to the ISM by dying stars, the slow winds of evolved giant stars, the planetary nebulae of dying low-mass stars, a trickle of gas from stellar mass loss that has been ongoing since the stellar population aged off the main sequence. It is not replenishment in any meaningful sense. It is a slow, ongoing bleed of material from old stars back into an ISM that has nothing useful to do with it. The circumgalactic medium around the remnant is hot. This is not a temporary condition. The virial temperature of the halo, the temperature to which infalling gas is heated by the virial shock at the halo boundary, is, for a halo of 10 to the 13 or 10 to the 14 solar masses, in the range of 10 to the 7 Kelvin. At this temperature, the cooling time of the gas is longer than the Hubble time in the outer regions of the halo, and longer than a few billion years in the inner halo. The CGM is not cooling. It is not raining down onto the disk. It is sitting in a quasi-static hot configuration that has been maintained for billions of years by the combination of the virial shock heating new infalling gas and the low-level AGN activity of the central black hole, preventing whatever cooling does occur in the denser inner regions from proceeding efficiently. The central black hole is still there. It is always still there, but it is not doing what it did during the merger, not accreting at high fractions of its Eddington limit, not driving the luminous quasar phase outflows that heated the CGM and drove gas from the galaxy in the early post-merger period. It is in what is called the radio mode, or the kinetic mode, or the maintenance mode, operating at a low accretion rate, releasing energy not primarily as radiation but as mechanical output, low-power jets that propagate outward into the hot halo gas, and deposit just enough energy to offset the slow cooling that does occur in the densest inner regions of the CGM. The balance is not perfect. It fluctuates. The cooling and heating rates vary spatially and temporally, but the net effect over billions of years is that the hot halo remains hot. The black hole is doing precisely what is needed to maintain the state, neither more nor less, and it will continue doing so for as long as the halo maintains the gas density needed to sustain even this low level of accretion. The morphology of the remnant, the spheroidal stellar distribution that the merger produced, is not changing on any timescale that matters for star formation. The stars are moving in their disordered orbits. The velocity of dispersion is what it was after coalescence. The effective radius is slowly growing as minor mergers add stars to the outer envelope, but none of this structural evolution involves the kind of dynamical event that would reorganize the stellar distribution into something with disk-like properties again. The tumorostability of whatever residual gas exists in the system is high. The spheroidal potential keeps it that way, and has been high for so long that even if the gas was somehow replenished, the structural barrier to star formation would still be present. What this object is, stripped of narrative, is a stable configuration of matter that has passed through a highly dynamic phase and arrived at a state of low activity that it will maintain for a very long time. The stars will continue to age. The more massive ones among the remaining population will eventually exhaust their hydrogen and evolve into giants and then remnants, white dwarfs, occasionally neutron stars, adding their mass to the slow stellar graveyard accumulating inside the remnant. The overall stellar mass will decline very slowly as mass is lost to stellar winds and supernova ejecta, some of it leaving the galaxy entirely, some of it cycling through the thin, warm ISM. The galaxy will dim, not quickly, Over billions of years, the integrated luminosity will decline as the main sequence stars slowly age toward the lower end of the stellar mass function, with the longest-lived stars persisting for timescales that dwarf the current age of the universe. It is, in some sense, finished. Though finished is not quite the right word, nothing about it suggests completion in the way a process can be complete. It is more that the dynamic phases are over. The mergers that built it, the starburst that consumed its gas, the AGN episodes that heated its halo, the morphological transformation that stabilized its remaining gas against collapse, all of that is in its past. What continues is maintenance, low-level accretion, slow stellar evolution, occasional minor mergers that add a small stellar population to the outer envelope without disturbing the interior, the hot halo being held at temperature by a black hole doing the minimum necessary. It began somewhere in its history as gas. Cold molecular corpuscles in the disks of two or more spiral galaxies, organized into giant molecular clouds, fragmenting into cores, collapsing into stars. Those stars lived and died and enriched the ISM with metals and returned gas to the system and contributed to the feedback that eventually ended the whole cycle. The galaxy that exists now is built from the remnants of that process. The stars that formed during it, the black hole that grew from it, the halo that was shaped by it. The gas that started everything is gone, not destroyed, locked. In stars that are no longer forming, in a halo that is no longer cooling, in a structure that is no longer fragmenting, in a black hole that is no longer accreting at a rate that would make anyone look twice. The merger finished a long time ago. The silence has been here ever since. This video exists because of the people on Patreon who chose to make it possible. Every single one of you. You are the reason this place exists.